Hello there, and welcome to Science for Sleep, where curiosity drifts quietly through the cosmos and science moves at a bedtime pace. Tonight, we're turning our gaze outward, past the quiet hum of your room, past the soft glow of your screens, and into the dark stretch of everything that exists. Because somewhere out there, farther than any telescope can see, the universe itself is doing something rather strange. It's expanding. Not just a little, not just now and then, but constantly, quietly, relentlessly stretching itself wider and wider. And that simple fact that the universe won't sit still might be one of the most mysterious and important things we've ever learned. Before we get lost among the galaxies, let me ask you something. Where are you listening from tonight? Is it early morning for you? The kind of hour when the sun hasn't yet decided if it wants to rise? Or maybe it's late, the world around you slowing down, and you're here letting your thoughts wander somewhere between science and sleep. Either way, I'm glad you're here. And if you find these cosmic conversations a peaceful way to unwind, I'd be grateful if you gave this little corner of calm a like, maybe even subscribed. It helps more wandering minds find their way here, to drift with us through the quiet mysteries of the universe. Now, let's settle in. Take a breath, maybe adjust your pillow or your blanket, and let's follow that strange idea that the universe is expanding. Because while it sounds simple enough, it's one of those truths that keeps unfolding the more you think about it. What does it even mean for space itself to stretch? What is it expanding into? And why is it happening at all? Imagine you could freeze everything for a moment. Galaxies, stars, planets, you, me, all suspended in place. If you could look at the entire universe at once, you wouldn't see empty blackness with little dots floating in it. You'd see a web, a vast structure of filaments and clusters, like threads of glowing pearls stretching through space. And between those threads, enormous gaps, dark voids where almost nothing exists. It looks a little like soap bubbles packed together, the bright galaxies outlining the thin walls between emptiness. This pattern isn't static. Over billions of years, those galaxies have been moving farther apart, carried away not by motion through space, but by the expansion of space itself. This is the key idea. The universe isn't expanding into something. Space itself is growing. It's as if the distance between points is increasing, even though each point stays where it is. Astronomers often use the image of a balloon. Imagine you draw little dots on the surface of a balloon, each dot representing a galaxy. When you blow up the balloon, the dots move farther apart, not because they're crawling across the surface, but because the surface itself is stretching. Now, the universe isn't a balloon in any ordinary sense, and it doesn't have an edge or a center like a balloon does. But the analogy helps. Every part of space is expanding, and that means every distant galaxy is moving away from every other one. It's an unsettling idea, especially when you remember that for most of human history, we thought the universe was fixed and eternal. The stars we saw at night were comforting in their constancy. They rose and set, but they didn't go anywhere. To early observers, the heavens looked like a perfect dome, unmoving and timeless. Even as we learned that the Earth was spinning, orbiting, and drifting through a galaxy, there was still an assumption that on the larger scales the universe must be steady. After all, how could everything, literally everything, be moving away from everything else? For centuries, that idea didn't even cross our minds. Ancient astronomers built their models around stability. Aristotle imagined an eternal cosmos, where change only happened in the realm of the Earth, not in the perfect heavens. Later, Newton's laws described a universe that worked like a vast clock, ticking along indefinitely, filled with stars and matter that might pull on each other but wouldn't expand or contract on a grand scale. Even when telescopes grew powerful enough to show that the Milky Way wasn't the whole universe, most astronomers still assumed that space was static. Then came a quiet revolution. In the early 20th century, just as Einstein was reshaping our understanding of gravity and space-time, astronomers began to notice something odd. about the light coming from distant galaxies. It was stretched, shifted toward the red end of the spectrum. This phenomenon, called redshift, meant that those galaxies were moving away from us. The farther away they were, the faster they seemed to be receding. This wasn't just a few wandering galaxies drifting apart, it was a pattern, a systematic stretching of light across the sky. And from that pattern, one man, Edwin Hubble, realized what it meant. The universe itself was expanding. It's hard to overstate how shocking that discovery was. It meant that space wasn't static or eternal, but dynamic and changing. It meant that if you wound the clock backward, all those galaxies would come closer and closer together until, billions of years ago, everything was once compressed into an unimaginably dense and hot state. That realization eventually led to what we now call the Big Bang theory. But the term bang can be misleading. It wasn't an explosion in space. There was no empty void waiting for the universe to burst into it. Instead, space itself was expanding everywhere at once. The Big Bang was the beginning of space and time themselves. Even Einstein had resisted this idea at first. His equations of general relativity, which describe how gravity shapes space and time, naturally predicted that the universe should either expand or contract. But he didn't like that. It didn't fit with the philosophical belief in a static cosmos. So he added a term, the cosmological constant, to balance things out and keep the universe steady. When Hubble's observations later confirmed that space was indeed expanding, Einstein reportedly called that extra term his greatest blunder. The universe hadn't needed to be forced into balance. It was already moving, growing, changing all on its own. And that's where the real mystery begins. Because once we knew the universe was expanding, another question naturally followed. Why? What's driving it? And, maybe even more puzzling, what keeps it going? When we think of movement, we usually think of something pushing or pulling. A car accelerates because an engine burns fuel. A ball moves because someone throws it. But cosmic expansion isn't like that. There's no engine in the middle of the universe pushing galaxies outward. There's no air rushing past or friction slowing them down. It's not that galaxies are flying through space. It's that the space between them is stretching, and once that process began, it has continued ever since. To understand why, scientists look to the conditions of the early universe. Immediately after the Big Bang, space was filled with incredibly hot, dense energy. Matter and radiation were mixed together, expanding rapidly. As the universe grew, it cooled, and that cooling allowed matter to form atoms, then gas clouds, then stars and galaxies. But the overall expansion never stopped. It just slowed down a bit as gravity began pulling matter together. Galaxies formed clusters, stars were born, planets coalesced, but on the grandest scales the stretching of space went on. If you could somehow travel back to those first few minutes after the Big Bang, you'd see a universe smaller than a galaxy, glowing with blinding radiation, expanding faster than you could comprehend. As time went on, it grew larger and more structured, eventually reaching the vastness we see today. But what's truly astonishing is that the expansion didn't just continue, it began to speed up again. That acceleration, discovered in the late 1990s, revealed something even more mysterious. Whatever's pushing the universe apart is stronger than the gravity trying to pull it back together. This invisible force is what we now call dark energy. No one knows exactly what it is. It doesn't seem to clump like matter, it doesn't emit light, and yet it makes up roughly 70% of the total energy content of the universe. It acts like a kind of pressure built into space itself, causing space to expand faster and faster. And the more space there is, the more dark energy there seems to be, which only speeds the process further. It's as though the universe has a built-in tendency toward expansion, an underlying rhythm that keeps stretching it wider no matter how long it's been playing. To make sense of this, astronomers use what's called the cosmological principle, the idea that on large scales the universe looks roughly the same everywhere. There's no special centre, no privileged edge. If you stood in a galaxy billions of light years away and looked out, you'd see the same kind of expansion we see from here. Every observer, no matter where they are, would see galaxies moving away from them in all directions. It's a hard concept to picture, because our minds naturally want to place things in a centre and an edge. But the universe doesn't work like that. It's more like the surface of that balloon, finite in what we can observe, but unbounded, stretching everywhere at once. As we observe this expansion, we're also looking back in time. The light from distant galaxies has taken billions of years to reach us, so when we see a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. That means we can actually watch the history of expansion written across the sky. The most ancient light of all, the cosmic microwave background, shows us what the universe looked like just 380,000 years after the Big Bang. At that time, it was a glowing fog of plasma, almost uniform, with tiny ripples that would eventually grow into galaxies. This faint radiation fills the universe even now, a soft afterglow of the moment when light could first travel freely through space. If you could tune your senses to that wavelength, a kind of microwave whisper, you'd be bathing in light from the dawn of time. It's everywhere, a relic of the first moments of expansion. And from its subtle variations, we've learned an extraordinary amount about the size, shape, and fate of the universe. We know it's expanding, yes, but we also know it's doing so at an accelerating pace. And that single fact changes everything about how we imagine the future. For billions of years, gravity and expansion have been locked in a kind of cosmic tug-of-war. Gravity pulls matter together, forming stars, planets, and galaxies, while expansion pushes everything apart. If gravity had been stronger, the universe might have eventually slowed and collapsed back in on itself in a big crunch. But the opposite is happening. Expansion is winning. And that means the universe's future will be one of continued stretching, cooling, and fading. Galaxies that are now visible to us will someday drift so far away that their light will never reach us again. The night sky will grow emptier, quieter, lonelier. But that's far, far in the future. For now, our local corner of the cosmos, our galaxy, the Milky Way, and its neighbours in the local group, remain gravitationally bound. They won't drift apart. Gravity will hold them together even as the universe beyond continues to expand. In fact, in a few billion years, the Milky Way and the Andromeda Galaxy will merge into a single, massive elliptical galaxy. The expansion of space affects the large-scale structure of the universe, not the bound systems within it. That's why you, sitting here now, aren't being stretched. The atoms in your body are held together by forces far stronger than cosmic expansion. The Earth doesn't grow, the solar system doesn't drift apart. On those scales, gravity and electromagnetism win. Still, when you look up at the night sky, every faint redshifted galaxy you see is a reminder that the universe is restless. It doesn't like to sit still. It's been expanding for nearly 14 billion years, and as far as we can tell, it will continue for billions more. Perhaps forever. And that brings us back to that simple but profound question. Why does the universe keep expanding? The best answer we have is that expansion is built into the very nature of space-time. It's not something that started and stopped. It's the geometry of the universe itself evolving over time. And whatever dark energy truly is, whether it's a property of the vacuum, a new kind of field, or something we don't yet have the language to describe, it seems to be the fuel that keeps the expansion going. The universe, it seems, is still breathing, and as we rest here, quietly thinking about that, the light from distant galaxies continues its long journey across the dark. Every second that passes, the space between those galaxies stretches a little more. The stars we see tonight are slightly farther away than they were yesterday, and tomorrow they'll be farther still. The change is almost imperceptible on human scales, but on cosmic time scales, it's enormous. The universe grows not in leaps, but in a slow, steady rhythm, one that has been pulsing since the beginning. It's a humbling thought that everything around us, from the atoms in our bodies to the galaxies at the edge of the observable universe, is part of that same expansion. We're not outside it, watching it happen. We're inside it, moving with it. Every breath we take, every second that passes, unfolds within this vast growing fabric. And while the scale of it is beyond imagining, there's a strange comfort in knowing that it's all connected, that even as the universe expands outward, it carries us gently along with it. For most of human history, when people looked up at the night sky, they saw permanence. The stars seemed to hang there, unmoving, fixed into familiar patterns that returned night after night, season after season. The sky was something to trust, something that didn't change. You could set your crops, your journeys, even your myths by it. The moon waxed and waned, the sun rose and fell, and the stars stayed where they were supposed to be. Everything above felt eternal compared to the fleeting things of the earth. The ground shifted, the seasons changed, but the heavens remained still. It's easy to understand why ancient people thought of the sky as a perfect sphere turning gently above a stationary world. To their eyes, the stars didn't move relative to one another. The constellations were like carvings on the inside of a great dome. The Greeks gave that dome a name, the celestial sphere, and imagined it rotating around us, carrying the stars in graceful, predictable circles. In many cultures, this vision of the sky as constant wasn't just a scientific idea, it was spiritual. The heavens were a symbol of order, an expression of something beyond the chaos of daily life. Night after night, the same constellations returned, the same belt of Orion, the same dipper pointing to the same pole. Even the planets, which wandered against the backdrop of stars, moved along set paths. Everything above seemed to follow rules, elegant, eternal rules. For early astronomers, that sense of stability was reassuring. The universe was a grand clock, its gears and wheels turning with mathematical precision. You could rely on it, and you could measure time by its motion. Of course, it wasn't truly still. The sky's apparent steadiness is a trick of scale and distance. Even now the stars are moving, racing through space at thousands of kilometers per second, orbiting the center of the galaxy like enormous celestial boats carried by invisible tides. But because they are so far away, their motion is imperceptible to the naked eye. Over the span of a human life, the constellations hardly change. Only across tens or hundreds of thousands of years do their patterns begin to drift. The Big Dipper, for example, hasn't always looked the way it does. Give it another 100,000 years, and it will be a very different shape entirely. Yet for us, living on shorter scales, it feels like the sky doesn't move at all. That illusion of stillness shaped how we thought about the universe. For thousands of years, the dominant belief was that everything revolved around the Earth, the geocentric model. It wasn't an unreasonable assumption given what people could observe. The stars rose in the east, set in the west, and returned again. The sun traced its arc across the sky in perfect rhythm. Even the wandering planets seemed to loop back in predictable patterns. To early minds, this motion was elegant and complete, a closed system with Earth at its calm center. When philosophers like Aristotle and later Ptolemy built their models of the cosmos, they did so with the assumption that the heavens were perfect, immutable spheres. The idea of stars moving independently through an infinite void would have seemed absurd. They were lights fixed to crystalline shells, their movements governed by divine harmony. And because the stars themselves seemed unchanging, the universe as a whole was imagined as eternal, no beginning, no end, just a grand mechanical order that had always been there. That belief endured for centuries. Even as new tools and methods emerged, the sense of cosmic stability remained deeply ingrained. When the telescope was invented in the early 1600s, it revealed astonishing detail. craters on the moon, the moons of Jupiter, the phases of Venus. But the stars still looked like points of light, fixed and distant. Galileo, Kepler and Copernicus all helped shift our perspective from Earth-centred to Sun-centred, yet even then, the larger universe was thought of as static. The planets moved. Yes, the Earth spun. The Sun might even travel through the galaxy. But the stars, the universe itself, seemed fixed in place. To many thinkers, this static view was comforting. It meant the universe was reliable, almost mechanical. Newton's laws described it perfectly. Matter attracted matter through gravity. The equations worked, and the whole thing could, in theory, run forever like a well-built clock. If the universe had a beginning, that was a question for philosophers, not physicists. The stars had been there before us and would remain long after. In that sense, astronomy was about mapping eternity, not evolution. And yet, even in that apparent stillness, the first clues of motion were hiding. When Isaac Newton studied gravity, he realized something subtle. Every star in the universe should attract every other star, just as the Earth attracts the moon. But if gravity were universal and eternal, then a static universe couldn't really exist. Sooner or later, everything should collapse inward under its own pull. Newton solved this paradox by assuming the universe was infinite and uniformly filled with stars so that every pull was balanced by another. It was a clever fix, but it was also an assumption, one that would quietly unravel in the centuries to come. By the 19th century, astronomers began noticing faint smudges in the night sky, what they called nebulae. Some of these were true clouds of gas, but others turned out to be vast collections of stars far beyond our own galaxy. The universe, it seemed, might be far larger than anyone had imagined. Still, even then, no one seriously thought it was expanding. The idea of a dynamic, changing cosmos simply didn't fit the worldview of the time. The laws of physics seemed too stable, too orderly, for something as grand as the universe to evolve. But as telescopes improved and spectroscopy, the study of light's composition, matured, cracks began to form in the illusion of stillness. Astronomers noticed that the light from certain distant objects was shifted toward the red end of the spectrum, a sign that they were moving away. This redshift pattern wasn't random. It followed a clear trend. The farther away an object was, the faster it appeared to be receding. Edwin Hubble would later confirm this relationship in 1929, but before that, others like Vesto Melvin Slipher had already begun collecting data that hinted at a universe in motion. When Hubble finally plotted the data, the picture became unmistakable. The galaxies were not static islands in a fixed space. They were racing away from one another, carried by the expansion of the universe itself. This realization overturned centuries of belief in a stable cosmos. The sky, which had once been the very symbol of permanence, turned out to be the stage for constant motion on the grandest possible scale. It's worth pausing to think about how that must have felt. Imagine dedicating your life to studying the stars under the assumption that they're unchanging, only to discover that the universe itself is moving beneath them, stretching everything apart. Even Einstein resisted the idea. When he developed general relativity, his equations implied an expanding or contracting universe, but he couldn't accept it. The thought of a non-static cosmos seemed wrong, almost unthinkable. So he introduced the cosmological constant, a kind of mathematical patch to keep the universe balanced and still. It was only when Hubble's observations confirmed the expansion that Einstein admitted his correction had been unnecessary. The universe, it turned out, wasn't balanced at all. It was restless. That restlessness continues today, and it's not subtle. Every second, the universe grows larger. Galaxies at the edge of what we can see move away from us at speeds approaching the speed of light. Their light stretches, reddens, and eventually fades beyond detectability. What looks like a still sky is actually a vast ocean of motion. The stars we see are drifting, the galaxies are separating, and even the fabric of space is expanding beneath it all. The illusion of stillness is just that, an illusion born of our tiny timescale and limited perspective. On human timescales, expansion is invisible. The Andromeda Galaxy, for instance, appears fixed in the sky, yet it's moving toward us at about 110 kilometers per second. In a few billion years, it will collide with our own galaxy, merging into a new one. Other galaxies, farther away, are receding at incredible speeds, but their motion is only detectable through their light. We live in a cosmos that changes constantly, but we're too small and too brief to see it directly. The stars look still because they are unimaginably far, and we are fleeting observers watching from a tiny planet that spins too quickly to notice the deeper tides of the universe. That's what makes the story of cosmic expansion so powerful. It reminds us that the calm we perceive isn't the whole picture. The sky may seem frozen, but it's alive with motion so vast and slow that only the collective patience of generations can reveal it. Every new telescope, every new survey, stretches our awareness a little farther and confirms what the data first whispered a century ago. The universe is expanding, and it always has been since its beginning. But what does it mean for something as enormous as the universe to be expanding? It's easy to imagine galaxies rushing through space like ships leaving a harbour, but that's not what's happening. Instead, it's space itself that stretches. The galaxies aren't moving through space as much as they are being carried along by its growth. The distances between them increase because the underlying fabric of reality expands. This is why there's no centre to the expansion. Every point in space sees every other point moving away, just as every dot on a balloon's surface moves away from every other as the balloon inflates. And yet, this motion doesn't affect everything equally. The Earth doesn't expand. The solar system doesn't expand. Even our galaxy, bound together by gravity, resists the stretching. Expansion only becomes apparent on the larger scales, where gravity's hold is weak and the vast voids of intergalactic space dominate. On those scales, the expansion of the universe shapes everything, from how light travels to how galaxies form to what the future of the cosmos will eventually be. When we talk about cosmic expansion today, we do so with precision instruments and complex mathematics, but at its heart the realization began with something very simple, noticing that the sky wasn't as still as it seemed. It began with curiosity, people looking up, comparing light, keeping records, asking why the same spectral lines shifted one way for some galaxies and another way for others. Bit by bit, the illusion of a static universe gave way to the truth of a dynamic one. And perhaps there's something poetic in that, even if we're keeping things grounded. For millennia, the stars represented constancy, but their motion revealed change to be the universe's most fundamental feature. Everything we see, from the faintest galaxy to the atoms in our bodies, exists within a reality that refuses to stay the same. The sky in motion became the first hint that the universe itself has a history, a past, a present, and a future, unfolding not just in time, but in space. And as we follow that motion outward, tracing it back to its origins, we find ourselves asking the next question. If the universe is expanding, if everything we see is drifting apart, where did that motion begin? What set it in motion in the first place, and how did the cosmos go from something unimaginably dense and hot to the vastness we now observe? For centuries, even after telescopes had revealed moons around Jupiter and the rings of Saturn, people still imagined the universe as something essentially complete. The stars might move in their distant orbits, the planets might wander, but the grand stage on which they moved was assumed to be fixed. The idea that the universe itself could be changing was, for a long time, almost unthinkable. It wasn't that no one wondered about beginnings or endings. It was that most scientists of the time had no reason to believe the cosmos as a whole did anything other than exist. It was simply there, vast, eternal, a kind of background reality that didn't need to move. That perspective began to shift in the early 20th century quietly at first. It didn't begin with an astronomer, but with a mathematician who redefined what space and time even meant. When Albert Einstein published his general theory of relativity in 1915, he changed how we think about gravity. It was no longer a force acting through empty space. It was the shape of space and time themselves bending under the influence of mass and energy. Massive objects like stars or planets curved the fabric of the universe, and other objects followed those curves. What looked like attraction was really geometry. Einstein's equations were revolutionary, but they carried an unsettling implication. When applied to the universe as a whole, they didn't describe something static. They suggested that space should be either expanding or contracting. A truly motionless universe wasn't stable. Gravity would eventually make it collapse, or an initial push would make it grow forever. Einstein didn't like that. The philosophical and cultural expectation of the time was that the universe was eternal and unchanging. So he added a term to his equations, a cosmological constant, to balance things out. This constant acted like a kind of anti-gravity, keeping the universe in equilibrium. He wasn't trying to hide anything, he was trying to make the math fit the world view. Meanwhile, far from theoretical physics, the astronomers of the early 20th century were busy with a very different question. What exactly were those faint patches of light they saw through their telescopes? The Milky Way was known to be vast, a sprawling disk of stars, gas and dust. But beyond it, observers kept noticing fuzzy spots that didn't resolve into individual stars, even with the best instruments. Some thought these were simply gas clouds within our own galaxy. Others suspected they might be entire systems of stars, what some called island universes. The debate went on for decades, quietly shaping the background of what would soon become one of the biggest revelations in science. In 1912, an astronomer named Vesto Melvin Slipher, working at the Lowell Observatory in Arizona, began taking detailed spectra of these spiral nebulae, as they were called. A spectrum is like a fingerprint of light. It shows the specific wavelengths emitted or absorbed by atoms in a star or galaxy. By comparing where those lines appear to where they should be, astronomers can tell whether an object is moving toward or away from us, and how fast. What Slipher found was strange. Many of the nebulae had their spectral lines shifted toward the red end of the spectrum. That meant they were moving away, and not slowly. Some were receding at hundreds of kilometers per second. A few were moving toward us, but the majority were flying outward. At first, Slipher didn't realize what he was seeing. The distances to these objects were still unknown, and the prevailing belief was that they were within the Milky Way. If that were true, their speeds would make no sense. Nothing inside a galaxy moves that fast relative to everything else. His data were curious, but without knowing how far away those nebulae were, they were just numbers, intriguing but inconclusive. Then came Edwin Hubble, working at the Mount Wilson Observatory in California, home to the world's most powerful telescope at the time. Hubble was methodical, patient, and obsessed with measuring distances. He used a class of stars called Cepheid variables, which pulse in brightness in a predictable way, to gauge how far away a galaxy is. The brighter the star and the slower its pulsation, the farther it must be. In the mid-1920s, after years of painstaking measurements, Hubble made an extraordinary announcement. The Andromeda Nebula, along with several others, wasn't a gas cloud within the Milky Way at all. It was an entirely separate galaxy, millions of light years away. The universe was not just vast, it was filled with countless other galaxies, each one an island of stars. That discovery alone would have been enough to redefine astronomy, but Hubble wasn't finished. He began combining his distance measurements with Slipher's velocity data. When he plotted the two together, distance on one axis, speed on the other, a clear pattern emerged. The farther away a galaxy was, the faster it was receding from us. The relationship was linear and strikingly consistent. Every direction he looked, the same trend appeared. Space wasn't static. The universe was expanding. It's hard to capture what a conceptual leap that was. In one stroke, it overturned centuries of assumption. The cosmos wasn't a serene, unchanging arena. It was dynamic, stretching, evolving. The light from distant galaxies wasn't just a snapshot of their position, it was a record of their motion through expanding space. Hubble's findings were published in 1929, and almost immediately, the implications began to ripple through both science and philosophy. Einstein himself visited Hubble at Mount Wilson soon after, and reportedly admitted that his introduction of the cosmological constant had been, in his words, his greatest blunder. The universe hadn't needed a balancing term to stay still. It wasn't balanced at all. It was in motion, growing larger every second. Though historians still debate whether Einstein actually used those exact words, the sentiment captures what many scientists felt at the time, a mixture of astonishment and humility. The universe, once thought eternal, had revealed itself to be restless. But that restlessness raised deeper questions. If the galaxies were all receding, if everything was moving apart, then at some point in the past, they must have been closer together. That line of reasoning led naturally to the idea of a beginning, a moment when the universe was compressed into an incredibly dense and hot state. The Belgian physicist and priest Georges Lemaitre was one of the first to propose this idea formally, describing it as the primeval atom, a single, compact origin from which space and time themselves expanded. His proposal was initially met with skepticism. Many scientists, including Hubble himself, preferred to avoid the notion of a cosmic beginning, but as the evidence grew, the picture became harder to ignore. The expansion implied not just motion, but history. The universe wasn't a static backdrop, it was a story unfolding. The galaxies weren't fixed in a cosmic architecture. They were participants in a continuous process. Even the light we see from them is stretched by the expansion of space, a phenomenon known as cosmological redshift. The wavelengths lengthen as the space between source and observer grows. What this means is that every photon reaching our telescopes carries a memory of the universe's growth. When you look at a distant galaxy, you're not seeing it as it is now, but as it was billions of years ago when the universe itself was smaller. That realization reframed almost everything. The night sky was no longer a picture of the present, it was a window into the past. The farther we look, the younger the universe appears. Distant galaxies are not only farther away, they are younger, their light stretched and dimmed by the long expansion that carried it to us. This is why modern cosmology is as much about time as it is about space. The universe isn't just expanding outward, it's expanding through its own history, layer by layer, light by light. The more astronomers studied the pattern, the more consistent it became. Every new observation confirmed it. The galaxies weren't randomly distributed. They followed the same rule. Distance and velocity were connected. That connection became known as Hubble's law, and it's still one of the cornerstones of cosmology. It tells us that space is stretching uniformly on the larger scales, and it provides a way to estimate the age and size of the universe. By measuring how fast galaxies are receding and how far away they are, scientists can calculate how long the expansion has been going on. Current estimates put that age at around 13.8 billion years, the time since the universe began expanding from its original hot, dense state. And yet, even as the evidence for expansion solidified, the underlying cause remained elusive. Why had it begun? What was pushing the universe outward in the first place? Early on, many thought of it like an explosion, the Big Bang, though that phrase, coined by the skeptical astronomer Fred Hoyle, was meant somewhat sarcastically. But the more carefully scientists examined it, the clearer it became that the Big Bang wasn't an explosion in space. It was the expansion of space itself. There was no center, no debris flying outward into emptiness. The entire universe expanded everywhere at once. Every point moved away from every other, not because of a force pushing them apart, but because the geometry of the universe itself was changing. To test this model, astronomers began looking for leftover traces of that early expansion. If the universe had once been hot and dense, it should still carry a faint afterglow, radiation cooled and stretched by billions of years of expansion. In 1965, two radio engineers, Arne Penzias and Robert Wilson, detected a persistent background noise in their antenna at Bell Labs. It came from every direction, at all times of day, and no amount of cleaning or recalibration could remove it. What they had stumbled upon was the cosmic microwave background, the cooled remnant of the early universe, now just a few degrees above absolute zero. It was the first direct evidence that the universe had indeed begun in a hot, dense state, and had been expanding ever since. The discovery of the cosmic microwave background confirmed what Hubble's data had implied. The universe wasn't static, and it hadn't always been the same. It had evolved, expanded, and cooled over billions of years. The restless cosmos wasn't just moving, it was aging, and that understanding transformed cosmology from a field of distant observation into one of dynamic history. Even now, the data keep refining the story. We've mapped the distribution of galaxies across hundreds of millions of light years, measured the cosmic background with exquisite precision, and traced the subtle imprints of the early universe in its structure. Everywhere we look, the same story emerges: expansion, motion, evolution. The universe, on the larger scales, behaves like something alive. It grows, changes, and carries the memory of its own beginnings in the light that fills it. And yet, the more we learn, the more questions appear. If the universe has been expanding for nearly 14 billion years, what determines how fast it expands? Has that speed always been the same? What happens to the expansion in the far future, when galaxies drift so far apart that their light never reaches one another? When you first hear that the universe is expanding, it's easy to imagine galaxies rushing through some kind of pre-existing emptiness, racing outward from a central explosion into a great void. It's a natural picture, because explosions are how we understand most kinds of expansion in daily life. If you throw a stone into a pond, waves spread across the surface. If a balloon bursts, fragments scatter outward through the air. But the universe isn't doing anything like that. There's no center, no outer edge, and no emptiness waiting beyond the stars. What's expanding isn't the stuff in the universe, but the very fabric of space itself. The distances between galaxies are increasing not because they're flying apart through space, but because the space between them is stretching. It's a subtle difference, but it changes everything about how we imagine the cosmos. When we say the universe expands, we're not talking about galaxies moving through a background. There is no background. The galaxies, the light, the vacuum, they're all part of the same expanding structure. It's as if reality itself is a flexible medium that can change scale. Distances grow, wavelengths stretch, and time itself flows differently depending on how that stretching unfolds. To understand this idea, it helps to return to something familiar, the balloon analogy. Imagine a balloon with tiny dots drawn on its surface, each dot representing a galaxy. As the balloon inflates, the dots move away from one another. The farther apart they are, the faster they seem to separate. But notice what's actually happening. The dots themselves aren't moving across the balloon's surface. They stay fixed in their own spots. What's changing is the surface itself. It's stretching. If you were one of those dots, you'd see every other dot moving away from you, and the more distant ones would seem to be receding faster. That's essentially what we observe in the universe. Of course, the balloon picture is only an analogy. The real universe isn't two-dimensional, and it doesn't expand into something else. The surface of the balloon has an outside, but space doesn't. When cosmologists talk about the expansion of space, they mean that the distance between any 2 points with no force holding them together increases over time. There's no need for an outside region to expand into. Space itself is growing everywhere at once. This idea is one of the most counterintuitive parts of modern cosmology, because it forces us to rethink what we mean by distance and motion. When you say two galaxies are moving apart, you might picture them travelling through space, like ships leaving a harbour. But on cosmic scales, that image breaks down. The galaxies are essentially at rest within their local regions of space. It's the metric, the mathematical description of distance, that changes. That metric, defined by general relativity, can evolve with time, and as it does, the distances between points in the universe change even though the points themselves remain in place. This is what Hubble discovered when he plotted the relationship between the redshift of galaxies and their distances. The farther away a galaxy is, the more its light is stretched, shifted toward the red part of the spectrum. This redshift isn't because the galaxies are rushing through space away from us like bullets from a gun. It's because as their light travels, the space that the light passes through expands. The wavelength of that light stretches along with it, like markings on a rubber band pulled slowly wider. The longer the journey, the more the stretch. That's why the most distant galaxies have the most redshifted light. We're not seeing them move away faster through space. We're seeing the imprint of the universe's growth on the light itself. In the language of physics, this stretching is described by something called the scale factor, a number that tells us how much the universe has expanded since a given time in the past. A scale factor of 1 might represent the present, while a scale factor of 1/2 would mean the universe was half its current size. When scientists say the universe has been expanding for about 13.8 billion years, they mean that this scale factor has been steadily increasing since the earliest moments after the Big Bang. The exact rate of that expansion is given by the Hubble constant, a value that tells us how fast galaxies are receding per unit of distance. The larger the distance, the faster the apparent recession, because more space lies between. It's worth pausing here to appreciate just how remarkable it is that we can measure this stretching at all. The universe is vast beyond comprehension. Galaxies billions of light years away emit light that has been travelling toward us for nearly the entire history of time. And yet, by carefully analysing the wavelengths of that light, astronomers can detect the subtle fingerprint of expansion, a shift so gradual that it's invisible to the eye but undeniable in the data. Every photon that reaches us carries evidence of how much the universe has grown since it began its journey. This stretching of space also affects how we think about speed. When we hear that distant galaxies are receding from us at tens of thousands of kilometers per second, or even faster than light, it sounds impossible. Nothing, we're told, can move faster than light. But these galaxies aren't breaking any cosmic speed limits. Their apparent motion isn't motion through space, it's the result of space itself expanding. The rules of relativity forbid objects from moving through space faster than light, but they don't forbid the fabric of space from stretching in such a way that distant objects end up farther apart faster than light could travel between them. In practical terms, this means that there are regions of the universe so distant that their light will never reach us, no matter how long we wait. The expansion of space between us and them is happening faster than the photons trying to cross it. Those regions are beyond our observable horizon. They exist, but they're forever out of reach. The universe, in that sense, is much larger than the part we can see. What we call the observable universe is just the region from which light has had enough time to arrive since the beginning. Beyond that horizon, the expansion carries everything away too quickly for light to ever catch up. On smaller scales, though, things behave differently. Inside galaxies, stars are held together by gravity. Inside solar systems, planets are bound by the pull of their suns. On these scales, the expansion of the universe is effectively zero. The forces that hold matter together are vastly stronger than the gentle stretching of space. That's why you're not expanding, your home isn't expanding, and even the Milky Way remains largely unaffected. The expansion only dominates on the enormous scales between galaxy clusters, where gravity's grip weakens and space itself takes over. To picture this, imagine dots connected by springs on a rubber sheet. If you gently stretch the sheet, the dots move apart, but the springs holding nearby dots together resist the pull. Those groups of dots stay bound while distant ones drift away. That's roughly how galaxies behave. The universe grows on large scales, but local systems remain intact. It's a kind of cosmic compromise between the expanding geometry of space and the self-gravity of matter. When cosmologists describe this expansion mathematically, they use what's called the Friedmann-Lemaitre-Robertson-Walker metric, or FLR-DIC for short. It's a model of the universe based on general relativity that assumes everything is, on average, the same in every direction, homogeneous and isotropic, as the terms go. This simplification allows scientists to describe how the scale factor evolves over time, depending on the contents of the universe, matter, radiation, and the mysterious energy that drives the acceleration of expansion today. It's a remarkable framework because with just a few parameters, it can describe the evolution of the entire cosmos from its earliest moments to the present day. But even without equations, the concept is surprisingly intuitive once you accept it. Everything that exists is part of this fabric. Galaxies, light, and the very vacuum are not separate things moving within a stage. They are parts of the stage itself changing together. When light travels across expanding space, it's not just crossing a distance. The distance itself is increasing as it moves. That's why light from the farthest galaxies is so faint and so stretched. By the time it reaches us, the universe has grown many times larger than when that light was emitted. The stretching of space also explains something else that might otherwise seem puzzling. The cosmic microwave background, the faint glow left over from the early universe, began as high-energy radiation. In those first moments after the Big Bang, the universe was dense and hot enough for light to have a wavelength thousands of times shorter than what we see today. As space expanded, those wavelengths stretched along with it, cooling the radiation into the microwave range. That's why we now detect it as a cold background signal rather than blinding light. The universe has literally stretched its own radiation into a lower energy form. This cooling through expansion is one of the key processes that shape the cosmos. As the universe grew, its temperature dropped. That cooling allowed particles to combine into atoms, gas clouds to condense into stars, and stars to forge the heavier elements that would one day form planets. Without the expansion, the universe would have remained hot, dense, and uniform. No structure, no galaxies, no possibility of life. The stretching of space isn't just a geometric curiosity. It's the reason the universe could evolve into something complex enough for us to exist and ask about it. Even now, this process continues. The cosmic web, that vast network of filaments and clusters stretching across billions of light years, is still shaped by expansion. The largest structures we can see are frozen snapshots of how matter responded to the universe's stretching and gravity's pull. Regions that were slightly denser in the early universe grew into clusters of galaxies, while emptier regions expanded faster and became the great cosmic voids. The balance between these forces, gravity pulling inward, space stretching outward, has been the quiet engine of cosmic evolution for billions of years. When astronomers measure this expansion today, they use a variety of tools. Supernovae, which are exploding stars that shine with predictable brightness, serve as cosmic mile markers. By comparing their apparent brightness to their intrinsic luminosity, scientists can measure how far away they are and how their light has been stretched. Other methods include mapping the subtle ripples in the cosmic background radiation and tracing the large-scale clustering of galaxies. All of these independent approaches point to the same conclusion. The universe is not just expanding, it's doing so faster than it used to. That acceleration, discovered in the late 1990s, implies that some form of energy permeates space itself, counteracting gravity's pull. This so-called dark energy behaves as if every cubic meter of space carries a tiny, constant amount of energy, and as space expands, there's simply more of it. The result is a feedback effect. The more the universe grows, the stronger the influence of this energy becomes. The galaxies move apart faster, the distances increase more quickly, and the process continues. In a sense, dark energy is an extension of the very concept we've been discussing, the stretching of space itself. If space can expand, it must have properties. It's not a nothingness, it's a dynamic field that can change, evolve, and carry energy. What we call dark energy might be an expression of those properties, a kind of built-in pressure that drives the universe's expansion ever onward. We don't yet know what it is, only that it seems to exist everywhere equally, filling the cosmos like an invisible wind that no one feels but everyone measures. The stretching of space isn't something we notice directly, but its fingerprints are everywhere. The redshift of galaxies, the faint microwave glow, the large-scale structure of the universe, even the way time passes differently in expanding space. All of it arises from this single, quiet phenomenon. It's one of those truths that becomes more astonishing the more you think about it. Every moment you spend alive, the universe grows a little larger. Every second, more space exists than the second before. The stars you see tonight are slightly farther apart than they were last night, and the light travelling toward you from distant galaxies is being stretched even as you listen to these words. And though the expansion is gentle on our scale, far too small to ever feel, it defines the grand rhythm of existence itself. Galaxies drift apart, clusters thin, light cools, and the cosmos grows older. The universe, from the smallest atom to the largest void, participates in that expansion. It's not a race or a burst, but a steady, almost meditative stretching, carrying everything forward into a future that grows wider with every passing heartbeat. Even as scientists continue to measure it, debate its rate, and refine the numbers, the deeper question remains: what started it, and why does it continue? If space can stretch, then something must govern how and when it does. When scientists first realized that the universe was expanding, a question naturally followed. If everything is moving apart now, what happens if we trace that motion backward in time? Every galaxy that is receding must once have been closer. Every cluster, every atom, every grain of matter would at some point have been part of something smaller and denser. Push the timeline back far enough, and all the distances between things shrink towards zero. That simple idea led to one of the most profound insights in all of science, that the universe had a beginning. But beginnings in cosmology are never simple. It wasn't just that the matter we see today once occupied a smaller space. It was that space itself was smaller. Time itself was younger. The early universe wasn't an explosion of matter into emptiness. It was the birth of space and time expanding together. The further back you go, the denser and hotter the cosmos becomes, until you reach a point where our current physics begins to falter. That moment, the one we call the Big Bang, wasn't so much an event in time as it was the origin of time itself. For decades, scientists debated whether the universe truly had such a beginning. Many found the idea unsettling, preferring a cosmos that had existed forever. The notion that the universe might have a finite age raised uncomfortable questions about what, if anything, came before and how such an origin could occur. Others, like Georges Lemaitre, found it elegant, a natural outcome of Einstein's equations and the expansion Hubble had observed. Still, it remained largely theoretical. There was evidence that the universe was growing, yes, but could we ever find traces of what it was like in its first moments? That answer came, almost by accident, from a faint and persistent whisper that fills the entire sky. It isn't a sound you can hear with your ears, but a glow you can detect with radio telescopes, a constant background of microwaves coming equally from every direction. This radiation is called the cosmic microwave background, or CMB for short. It is, quite literally, the afterglow of the Big Bang, the cooled and stretched light left over from a time when the universe was still young. To understand what this radiation represents, imagine the universe not as it is now, but as it was around 380,000 years after the Big Bang. That's unimaginably long ago, yet by cosmic standards it's early, just an infant phase. The universe then was filled with a hot, dense plasma of particles. Protons, electrons and photons all mixed together in a blinding fog. At those temperatures, atoms couldn't form. Every time an electron tried to settle into orbit around a proton, the intense radiation would knock it loose again. Light couldn't travel freely through that soup because it kept scattering off the charged particles. The universe was opaque, glowing and turbulent. As it expanded, though, it cooled. Gradually, the radiation lost energy, the temperature dropped, and the particles began to slow down enough for hydrogen atoms to form. When that happened, the universe suddenly became transparent. Light could now move freely through space without constant scattering. The moment when this occurred is called recombination, and the light released then has been travelling ever since, stretched by the expansion of space into the microwave part of the spectrum. That ancient light is what we detect today as the cosmic microwave background, a perfect snapshot of the universe as it was when it first became clear. In the mid-1960s, two engineers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, testing a large horn-shaped radio antenna built for satellite communication experiments. No matter what direction they pointed it, they picked up a faint background noise that wouldn't go away. They tried cleaning the antenna, checking the electronics, even removing what they thought might be pigeon droppings interfering with the signal. But the noise persisted. It was uniform, unchanging, and came from every part of the sky. At the same time, a few miles away, a group of physicists at Princeton University led by Robert Dicke were preparing an experiment to search for exactly that kind of radiation. When Penzias and Wilson heard about it, they called the Princeton team, and soon it became clear what they had found. That faint hum, that seemingly insignificant background signal, was the relic radiation of the early universe, the first light that ever travelled freely through space. It's hard to overstate the significance of that discovery. For the first time, scientists had direct evidence that the universe really did begin in a hot, dense state. The cosmic microwave background was the smoking gun of the Big Bang theory. It wasn't just a theoretical model anymore. It was something measurable, something that filled the sky with quiet proof of our origins. At first, the CMB seemed almost perfectly uniform. The temperature was the same in every direction to 1 part in 100,000. That uniformity was itself surprising. If the early universe had been chaotic or uneven, you would expect big variations in the radiation. Instead, it was astonishingly smooth, implying that whatever the universe was like in its first moments, it had somehow reached a state of near-perfect equilibrium. That raised a new puzzle. How could regions so far apart have become so uniform when there hadn't been enough time for light to travel between them? That question would later lead to ideas about cosmic inflation, a brief period of incredibly rapid expansion right after the Big Bang. As instruments improved, scientists began detecting tiny variations in the CMB, fluctuations in temperature and density that correspond to the seeds of galaxies and clusters we see today. These faint patterns, mapped in exquisite detail by missions like COBE, Dulles Map and later Planck, show how the early universe was not perfectly smooth after all. There were minute differences, slightly denser regions that gravity could later amplify into stars and galaxies. In those tiny ripples of ancient light, we can see the blueprint of all cosmic structure. When you look at one of those maps of the CMB, covered in subtle patches of blue and red, you're essentially looking at the universe's baby picture. Each variation represents a place where matter was just a little more concentrated or a little less so. Over billions of years, those small differences grew, shaping everything that followed. Without them, the universe would have remained a diffuse fog of hydrogen and helium, with no galaxies, no planets, and no observers to wonder where it all came from. The temperature of that background radiation today is about 2.7 Kelvin, just 2.7 degrees above absolute zero. It's the faintest possible glow, but it fills all of space. If your eyes could see microwaves, the night sky would never look dark. It would shimmer faintly with that primordial light, the same in every direction. That's what makes it so extraordinary. No matter where you point your telescope, you're looking into the same past. Every part of the sky carries the same echo from the universe's earliest time. When cosmologists analyse the CMB, they extract an astonishing amount of information. From its temperature fluctuations, they can infer the universe's age, its composition, its geometry, and its rate of expansion. The pattern of those fluctuations tells us how much matter and energy exist in different forms: ordinary matter, dark matter, and dark energy. The fact that the data fits so precisely with theoretical predictions is one of the strongest confirmations of modern cosmology. It shows that the same physical laws we test in laboratories today were already at work in the earliest universe. But beyond its technical importance, the CMB has a quiet beauty to it. It's the oldest light we can ever hope to see. No telescope, no matter how powerful, can look beyond it, because before that moment of transparency, the universe was opaque. Light simply couldn't travel. In a sense, the CMB marks the edge of our visible universe, not because there's nothing beyond, but because that's the point where light first became free to move. Beyond it lies the realm of theory and imagination, the domain of energies and densities so extreme that our equations struggle to make sense. And yet, even though we can't see past that veil, the echoes that reach us are enough to reconstruct much of what happened before. From the way the CMB's tiny ripples align, we infer that the universe underwent an incredibly brief but powerful burst of inflation a fraction of a second after the Big Bang. During that period, space expanded exponentially, smoothing out irregularities and setting the initial conditions for everything that followed. That expansion was so rapid that regions once close together were stretched beyond each other's horizons. When inflation ended, the universe continued expanding more slowly, cooling, and eventually giving rise to the light we now see as the CMB. In that sense, the CMB isn't just an echo of light, it's an echo of inflation itself, a lingering fingerprint of how the universe's earliest expansion unfolded. The tiny variations we observe today may even contain clues about quantum fluctuations that existed in those first instants, magnified to cosmic scales. If that's true, then the patterns in the microwave background are literally the fossilized remnants of quantum events that occurred when the universe was less than a trillionth of a second old. It's humbling to realize how much of our cosmic history is preserved in this faint radiation. Every photon of the CMB has been travelling for nearly 14 billion years, unaffected by anything except the slow stretching of space. It has passed through forming galaxies, crossed vast voids, and been bent slightly by gravity, but it still carries the imprint of the early universe with astonishing clarity. When you detect it, you are touching something almost unimaginably old. Light that began its journey long before there were stars, before there were planets, before there was even darkness as we know it. And the most extraordinary thing is that this ancient light is everywhere. It doesn't come from a single point or even from distant galaxies. It comes from every direction equally, because it was released everywhere equally. Every spot in the universe was once glowing, and that glow has been stretched and cooled until it fills all of space uniformly. Wherever you stand, whatever direction you look, you are surrounded by the afterglow of creation itself. This is what astronomers mean when they say the universe has no centre. There's no special location where the Big Bang happened. It happened everywhere, because everywhere was part of that early dense state. The CMB reminds us that the universe doesn't expand into something, it expands within itself. Every observer on every distant galaxy would see the same uniform radiation, the same gentle echo from the same beginning. When you think about it that way, the cosmic microwave background becomes more than just data. It becomes a kind of universal memory, a record of what the cosmos once was, written in light that never stops travelling. It's as if the universe never stopped whispering its origin story, carrying it forward through time for anyone, anywhere to listen. And just as those photons continue their endless journey, so too does the expansion that set them free. The universe didn't stop stretching when that light was released. It only slowed for a time as gravity began to pull matter together. Stars would form, galaxies would grow, and new structures would emerge. But the faint glow of the CMB never faded entirely. It became the quiet background of everything, a soft reminder that even the emptier space is filled with the memory of the beginning. As we trace those echoes and decode their patterns, we find not only the history of the universe but hints of its fate. The same expansion that stretched those ancient waves continues to act today, accelerating once more under the influence of dark energy. The CMB tells us where we came from, but it also helps us understand where we're going. And somewhere between that past and future lies the present, the moment we inhabit, in a universe that's still stretching, still cooling, still carrying the light of its first moments into the endless night. And if you listen closely, in that quiet, ongoing expansion, there's still a kind of hum, not in sound, but in the rhythm of existence itself. The galaxies drift, the light stretches, and the background glow continues, faint but unwavering. It's the same hum that began at the dawn of time and has never stopped since. The universe remembers its beginning, and in that memory it keeps expanding, carrying those first echoes ever outward, one wavelength at a time. When the universe first became transparent, when that faint afterglow of the cosmic microwave background began its endless journey through space, it marked more than just the cooling of matter. It marked a turning point. Before that moment, everything was light and plasma, too hot and chaotic for structure to exist. But as the cosmos expanded and cooled, something new began to happen. Particles that had been trapped in a dense, blinding sea of energy could finally settle into more stable forms. The universe, for the first time, could begin to build things. Those first few 100,000 years were a kind of cosmic infancy. Imagine a world without stars, without planets, without even darkness in the way we know it. Space was filled with a warm glow, a uniform haze of hydrogen and helium gas that stretched in every direction. The temperature was still thousands of degrees, but compared to the fiery density of earlier times, it was cool enough for atoms to exist. Protons captured electrons to form hydrogen, and the universe transformed from a fog of charged particles into a vast, transparent expanse of neutral gas. This transformation allowed light to travel freely, and that light, the same we now detect as the cosmic microwave background, carried with it a frozen record of the conditions of that time. But while the photons streamed outward, the matter they left behind began its long process of falling together under gravity. It was the first act of creation on a grand scale. The early universe wasn't perfectly uniform. Those tiny fluctuations in density, 1 part in 100,000, provided the seeds from which everything else would grow. Regions that were slightly denser had a bit more gravity. Over time they began to pull in more gas, and that gas in turn pulled in more of itself. The process was slow, almost unimaginably slow, but it was steady. The smooth fog of the early universe began to clump. Gravity has no patience for perfection. It takes even the smallest imbalance and amplifies it. As millions of years passed, these denser regions grew into long, thin filaments connected like threads in an invisible web. Between them, great voids formed, emptying out as matter flowed toward the denser nodes. This was the beginning of the cosmic structure we now see, the vast web of galaxies and clusters that defines the large-scale shape of the universe. But long before galaxies took form, something else had to happen. The first generation of stars had to ignite. In those collapsing clouds of hydrogen gas, As matter fell inward, it heated up. The increasing pressure raised the temperature until it reached millions of degrees. At that point, the protons in the gas began to fuse, releasing energy in a self-sustaining reaction. The first light of starlight shone through the universe, piercing the darkness for the first time. These first stars were nothing like the ones we see today. They were enormous, hundreds of times the mass of the sun, burning hotter and brighter, but also living far shorter lives. They formed from pure hydrogen and helium, with none of the heavier elements that later generations would carry. Their light flooded the universe, and their short, violent lives shaped everything that followed. When they reached the end of their lives, they exploded in titanic supernovae, spreading the first heavy elements, carbon, oxygen, iron, into the surrounding gas. Those elements would later become the raw material for planets, for oceans, for life itself. This period, when the first stars were born, is sometimes called the cosmic dawn. It began perhaps 100 million years after the Big Bang and marked the universe's transition from simple to complex. Before then, everything had been smooth and featureless. Afterward, the universe became textured, varied, alive with light. The radiation from those first stars also began to reionize the surrounding hydrogen, stripping electrons from atoms once again and making the universe partially transparent in new ways. That era of reionization ended the long cosmic night that had followed the cooling of the early plasma. To imagine what this transformation looked like is to picture a vast, expanding sea of darkness slowly coming alive with scattered points of light. The first stars, emerging like sparks from a cooling fire. Each one lit up its corner of the universe, carving out bubbles of ionized gas around it. Over hundreds of millions of years, these bubbles grew, overlapped, and merged until the entire universe was once again filled with light. As these early stars lived and died, they began to cluster under gravity, forming the first galaxies. The process was chaotic and violent, with smaller galaxies merging to form larger ones. Over billions of years, this merging built the structures we see today, spirals, ellipticals, clusters of thousands of galaxies bound together by gravity. But it all began with those first brief bursts of starlight. It's remarkable to think that everything we know, every atom in your body, every planet, every cloud, every stone, can trace its origins back to those first stars. When they exploded, they scattered heavy elements into the interstellar medium, enriching the gas from which later generations of stars and planets would form. The calcium in your bones, the oxygen in your lungs, the iron in your blood, all were forged in the cores of those ancient stars and returned to space through their deaths. You are, quite literally, built from the ashes of the first light. But before those stars, before any of that complexity, there was a time when even atoms didn't exist. A time when the universe was still a roaring fireball of pure energy and plasma. To understand how we got from that to the calm, structured universe we see now, we have to go back even further, into the first seconds after the Big Bang, when the rules of physics as we know them were only just taking shape. In the first fraction of a second, the universe underwent an extraordinary phase called inflation. Space expanded exponentially, faster than light could travel, smoothing out any irregularities and creating the uniformity we observe in the cosmic microwave background. In less than a blink, regions smaller than an atom were stretched to cosmic scales. When inflation ended, the energy driving it was converted into a hot, dense soup of particles. Quarks, electrons, photons, neutrinos, everything that would eventually become matter and radiation. As the universe continued to expand and cool, quarks combined to form protons and neutrons, and within minutes, those particles fused into the first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium. This process, called primordial nucleosynthesis, produced the basic chemical ingredients of the cosmos. But at that stage, the universe was still too hot for atoms to exist. It would take hundreds of thousands of years of further cooling before electrons could join those nuclei to form neutral atoms, allowing light to travel freely. That long cooling period was the universe's first deep breath, a gradual transition from chaos to structure. The energy that had once been concentrated in an unimaginably dense point had spread across a vast, expanding space. The violent roar of the early fireball faded into a faint background hum. That hum, stretched by the expansion of space, is the same radiation we detect today as the CMB. It's as if the universe's birth cry never truly stopped, only deepened in tone until it became the quiet microwave whisper that fills the sky. It's easy to forget when looking at the tranquil night sky that this calmness was born from such violence. Every calm starfield, every peaceful nebula is the descendant of an era when energy and matter were one, when the universe's temperature was measured in billions of degrees, and when even the forces of nature themselves were still differentiating. The strong nuclear force, the weak force, electromagnetism and gravity, all of them emerged from the same unified conditions as the cosmos cooled. The structure of reality itself crystallized out of that early chaos. For the first few minutes after the Big Bang, the universe was hot enough for nuclear reactions to take place everywhere. Every cubic centimeter of space was like the core of a star. As it cooled, those reactions froze out, locking in the relative proportions of hydrogen and helium that still dominate the universe today. Roughly 3/4 hydrogen, 1/4 helium, the elemental fingerprint of the Big Bang. It's a ratio that astronomers still measure in the oldest stars, a lingering clue to the conditions of those first moments. By the time the first million years had passed, the universe was a smooth, cooling expanse of gas. It was dark, but full of potential. The seeds of galaxies were already there, invisible in the density variations left over from the early universe. The first stars would not appear for hundreds of millions of years, but the foundation had been set. The universe had entered its long, steady expansion, and everything that would ever exist was already contained within it, not in form, but in possibility. Even now, when we look out into the deepest regions of space, we're seeing back into that past. The most distant galaxies we can observe are snapshots of what the universe looked like only a few 100 million years after its beginning. Their light has been stretched and dimmed by the expansion of space, but it still carries the story of the first structures taking shape. Each observation is like catching an echo of that birth cry, not in sound but in light, preserved across billions of years, and the echoes keep coming. Every photon, every neutrino, every trace of background radiation is a message from that early time. They tell us that the universe has been expanding steadily since those first moments, that it has cooled from trillions of degrees to just a few above absolute zero, and that it continues to stretch even now, driven by forces we only partially understand. The term Big Bang makes it sound like a singular explosion, a loud and sudden event, but what really happened was quieter, in a way, not an outward burst into emptiness, but a smooth unfolding of space and time themselves. It was the moment when the laws of physics began to operate, when space acquired its geometry and time its direction. Everything we experience, every heartbeat, every orbit, every second, traces back to that moment when the universe first began to expand. And if you think about it carefully, that expansion never stopped. It's still happening around you right now, on scales too large to notice. The distance between galaxies grows, the wavelengths of ancient light stretch, the universe breathes outward in a steady rhythm that has continued unbroken since that first instant. The same forces that shape the first atoms are still shaping the large-scale structure of the cosmos today. We live in the quiet aftermath of that birth cry. The roar has faded into background radiation, the plasma has cooled into stars and planets, and the chaos has settled into order. But the memory of that origin is everywhere. It's in the faint microwave hiss that fills the sky. It's in the abundance of elements measured in stars. It's in the smooth expansion that carries galaxies apart. The universe doesn't remember in words or images, but in patterns of energy and matter, in the faint imprints left by its own creation. Every observation we make, every telescope image, every spectrum, every measurement of cosmic expansion, is another way of listening to that long-echoing sound. The universe may have started with a single, brief burst of creation, but that burst never truly ended. It just changed form. The initial energy condensed into matter. The matter formed stars. The stars forged heavier elements, and those elements became the building blocks of everything that now exists. The process of creation continues, slower and cooler, but still moving forward. If you could somehow step outside of time and watch the entire history of the universe unfold from beginning to end, you'd see it as one continuous expansion, one smooth flow from density to vastness. The light of the first stars, the glow of the CMB, the galaxies drifting apart, all of it part of a single movement that began nearly 14 billion years ago and hasn't stopped. The birth cry of the universe wasn't a single shout, but a long unbroken song, still playing, still stretching outward into the dark. And as we continue to study that expansion, tracing it from its earliest moments to the vast structures we see today, we start to realize that this motion, this steady growth of space itself, might hold the key not just to the universe's past, but to its future. What began as a burst of creation has turned into an ongoing expansion that shows no sign of stopping. If the universe's birth cry was expansion, then its quiet companion has always been gravity, the invisible, patient force that tries to hold everything together. Expansion drives outward, gravity pulls inward. Between those two motions lies the balance that has shaped everything that has ever existed. For billions of years, this tug-of-war has been playing out on every scale, from the collapse of gas clouds into stars to the slow drift of galaxies across the cosmic web. Without gravity, there would be no structure, no stars, no planets, no life. Without expansion, there would be no time for any of those things to form. The two forces are opposites, but together they have written the universe's story. When we think about gravity, it's easy to imagine it as something simple, a pull between masses, a force that keeps us on the ground and the planets in their orbits. But on the scale of the cosmos, gravity becomes far more than a local attraction. It is the architect of everything. In the early universe, when matter was still evenly spread, gravity began to gather it. Those tiny fluctuations in density that appeared after the Big Bang, small ripples in the otherwise smooth sea of gas, became the seeds of galaxies because of gravity's relentless pull. Wherever there was a little more matter, gravity made it grow denser. The denser it became, the stronger the pull. Bit by bit, gravity sculpted the chaos of the early universe into structure. The process was slow but inevitable. As the universe expanded and cooled, gravity began to take hold more effectively. The densest regions stopped expanding with the rest of space, collapsing inward instead. Gas collected into halos of dark matter, an invisible form of mass that doesn't emit light but makes up most of the universe's matter content. Inside these halos, the first stars ignited, forming the earliest galaxies. Everywhere else, gravity continued its work, binding galaxies into clusters and clusters into superclusters, threading the cosmos together into the vast filaments and voids we now observe. For a long time, cosmologists assumed that gravity would eventually win this competition. If the universe had begun with an expansion, then gravity, acting on all the matter within it, should slowly pull that expansion back. Over billions of years, the outward motion would slow, just as a ball tossed upward eventually stops before falling back down. The question was how strong gravity's tug really was, and whether the universe contained enough matter to halt its growth entirely. That question defined cosmology for much of the 20th century. Scientists debated three main possibilities. If there were enough matter, enough gravitational pull, the expansion would eventually stop and reverse, leading to a collapse known as the Big Crunch. In that scenario, the universe would someday end as it began, in heat and density, a mirror image of its birth. If there were too little matter, gravity would never be strong enough to stop the expansion, and the universe would continue to grow forever, its galaxies drifting apart into a cold, dark emptiness. And if the amount of matter was exactly balanced, the universe would expand forever, but at an ever-slowing rate, asymptotically approaching stillness without ever truly stopping. Each of these outcomes depended on the same delicate balance: the competition between gravity's inward pull and the expansion's outward push. For decades, astronomers tried to measure which was winning. They mapped galaxies, estimated their masses, and calculated how fast the universe was expanding. It was an enormous challenge because the forces involved act over cosmic timescales. The expansion rate we measure today tells us how the universe is moving now, but gravity's influence unfolds over billions of years. What made the question even more complicated was that most of the universe's mass isn't visible. The stars we see account for only a small fraction of the total. The rest, as it turns out, is dark matter, something that neither emits nor absorbs light, but reveals itself through gravity. We can see its effects in the way galaxies rotate, in the way clusters bend light from background galaxies, and in the large-scale structure of the universe. Without it, galaxies would fly apart. Their stars simply move too fast to be held together by visible matter alone. Dark matter, whatever it is, provides the gravitational glue that holds galaxies together and gives shape to the cosmic web. Even with dark matter included, though, gravity appeared to be losing the grand contest. Observations in the late 1990s revealed that instead of slowing down, the universe's expansion was speeding up. The discovery came from studying distant supernovae, exploding stars that serve as precise cosmic distance markers. By measuring their brightness and redshift, astronomers could trace how the expansion rate changed over time. To their surprise, the data showed that galaxies were receding faster now than they had billions of years ago. Gravity's gentle tug wasn't enough. Something was pushing the universe apart, and whatever that something was, it was stronger than gravity on the larger scales. That something became known as dark energy, a term as simple as it is mysterious. It appears to act as a property of space itself, a kind of built-in energy that causes the expansion of the universe to accelerate rather than slow. Its discovery transformed cosmology. Instead of expecting gravity to one day pull everything back together, scientists had to face the possibility that the universe might continue expanding forever, not slowing, but speeding, its galaxies drifting ever farther apart until only silence remains. Still, even as dark energy dominates the universe's large-scale fate, gravity remains its sculptor. Without it, the accelerating expansion would leave behind only uniform emptiness. Gravity's role is what gives the cosmos its texture. It's the reason galaxies exist at all, the reason stars form, the reason planets can orbit. Wherever matter gathers, gravity takes over, overwhelming expansion on local scales. That's why our galaxy, and every other, remains intact even as the space between galaxies stretches. Gravity's reach may weaken with distance, but within its domain, it is unyielding. To see gravity's quiet power, you only have to look at how it shapes everything we observe. A cloud of hydrogen in space may be diffuse and invisible, but if left undisturbed, gravity will slowly pull it together. The cloud will grow denser, heat will build, and eventually a star will ignite. That same process repeats everywhere. Gravity doesn't rush, it doesn't demand attention. It simply works patiently over vast stretches of time. The same force that holds you to the Earth's surface is the one that binds galaxies across millions of light years. It's the same law, acting with the same consistency from the smallest pebble to the largest cluster. Einstein's theory of general relativity revealed that gravity is not truly a force in the conventional sense, but the curvature of space-time caused by mass and energy. When you place a massive object in space, it bends the geometry around it. Other objects move along those curves, following what we perceive as attraction. On cosmic scales, this means that the entire universe's structure, its shape, its fate, even the paths light takes, is determined by how matter and energy curve space. It's a beautiful idea because it connects everything in one elegant framework, gravity as the architecture of existence. Yet for all its elegance, gravity is astonishingly weak compared to the other forces of nature. The attraction between two masses is tiny, unless at least one of them is enormous. You can lift a paperclip off a desk with a small magnet, overcoming the entire planet's gravitational pull on it, and still, across billions of light years, gravity dominates the evolution of the cosmos. That's because it's cumulative. Every bit of matter, every particle adds to its effect. Over time, those tiny pulls add up, weaving galaxies together and shaping the universe's web-like pattern. Gravity also plays an unexpected role in the universe's expansion itself. While it can't stop the overall stretching of space, it influences how that stretching unfolds. Dense regions expand more slowly because gravity resists it, while emptier regions expand faster. This difference contributes to the growth of structure, matter clumping in some areas while voids balloon in others. In this way, gravity and expansion are not just competing, but collaborating. Expansion provides the stage. Gravity arranges the scenery. It's easy to think of gravity as something static, an unchanging law, but the way it behaves depends on the contents of the universe. In the early cosmos, when matter and radiation dominated, gravity's influence was stronger relative to the overall energy density. It slowed the expansion, allowing galaxies to form. Today, as dark energy takes over, gravity's relative strength on the larger scales diminishes. The expansion accelerates, but gravity continues its local work. Stars still form, planets still orbit, black holes still grow. Black holes are perhaps the most extreme expression of gravity's power. They are regions where space-time curves so steeply that nothing, not even light, can escape. In a sense, they are gravity's own victory over expansion, places where matter collapses beyond any chance of spreading apart. Inside galaxies, black holes anchor their surroundings, influencing the motion of stars and the dynamics of gas. Even though they make up only a tiny fraction of the universe's mass, their role as cosmic centers gives structure to the systems around them. In the larger cosmic picture, gravity's gentle tug is also what keeps our perspective grounded. It defines what near and far mean. It determines how galaxies cluster and how we perceive the expansion of the universe. Without gravity, the expansion would be uniform and featureless, a smooth, endless dilution. With gravity, the universe has a rhythm. Galaxies form, merge, and evolve. Stars live and die. The cosmos becomes a place not just of motion, but of history. Every time we look at the night sky, we're seeing the outcome of gravity's long patience. The stars we see are balanced between two competing processes, gravity pulling inward, fusion pushing outward. When that balance tips, a star collapses or explodes, spreading new elements into space which then become part of new stars. Gravity creates cycles within the broader expansion, turning the overall growth of the universe into something richly layered and self-renewing. Even time itself, in a sense, is shaped by gravity. The stronger the gravitational field, the slower time flows. Clocks near massive objects tick slightly slower than those in weaker fields, a phenomenon confirmed by both theory and experiment. It's a subtle effect on Earth but significant near massive stars or black holes. On cosmic scales, it means that time and gravity are intertwined in ways that still challenge our intuition. The very passage of time is part of gravity's influence. In the end, gravity's role in the expanding universe isn't to fight the expansion completely, but to shape what happens within it. It forms galaxies and clusters, creates stars and planets, and holds them together long enough for complexity to arise. Without it, the expanding universe would be nothing more than a featureless haze, a sea of drifting particles spreading endlessly apart. Gravity gives that expansion meaning, turning motion into form and chaos into structure. Even now, as the universe's acceleration continues, gravity hasn't gone silent. It remains the sculptor of the visible cosmos, quietly working within the spaces left between expansion's outward flow. Galaxies still merge, stars still collapse, matter still gathers in invisible halos that bend the light passing through them. Expansion may carry everything apart, but gravity ensures that in every corner of space something still comes together, and somewhere between those two forces, the steady stretch of expansion and the constant pull of gravity, lies the delicate balance that defines the universe we inhabit. It's the balance that lets galaxies exist long enough for stars to form, that lets stars shine long enough for planets to develop, that lets planets orbit long enough for life to arise, and wonder why anything exists at all. The universe, in its quiet way, has always been a conversation between gravity and expansion. One tries to gather, the other to scatter. Neither wins completely. Instead, they shape one another, each giving the other meaning. And as the expansion continues, carrying galaxies ever farther apart, gravity's imprint remains on everything that has formed. It's the gentle tug beneath the grand stretch, the invisible thread that connects the earliest atoms to the stars that will shine long after our own have faded. For most of the 20th century, astronomers assumed the universe's expansion must be slowing. It was simply common sense. The Big Bang had set everything in motion, and gravity, though gentle, would gradually tug on all that matter, pulling galaxies toward one another, slowing their outward drift. The universe might never collapse completely, but surely it wouldn't keep expanding at the same pace forever. Just as a ball thrown upward loses speed against the pull of Earth, the cosmic expansion should eventually decelerate under the pull of gravity. That was the expectation, logical, mathematical, and comforting in its symmetry. And then, it didn't happen. When the first solid measurements came in during the late 1990s, they revealed something entirely different. Instead of slowing, the expansion of the universe was speeding up. Distant galaxies weren't just receding, they were receding faster and faster over time. It was as if the universe had ignored gravity altogether, as if some unknown force was quietly pushing everything apart. What began as a search to measure the rate of cosmic slowing became a discovery that upended nearly everything we thought we knew about how the universe works. To understand how this was discovered, it helps to imagine how astronomers measure cosmic motion. The key lies in light, specifically in how it stretches. When a galaxy moves away from us, its light shifts toward longer wavelengths, a phenomenon called redshift. By measuring that redshift, astronomers can determine how fast a galaxy is receding. But distance is harder to measure. You can't stretch a tape across millions or billions of light years. Instead, astronomers rely on what they call standard candles, celestial objects whose intrinsic brightness is known. By comparing how bright they appear to how bright they should be, you can estimate how far away they are. One of the most reliable standard candles in the universe is a particular type of supernova known as type Ia. These are stellar explosions that occur when a white dwarf star, the dense remnant of a dead star, accumulates too much matter from a companion. When it reaches a critical mass, it ignites in a runaway thermonuclear blast, releasing an immense and consistent burst of light. Because the physics of these explosions are so uniform, astronomers can use them as cosmic yardsticks. In the 1990s, 2 teams of researchers set out to measure how fast the universe's expansion was slowing by observing these supernovae in distant galaxies. They expected to find that the more distant the supernova, the slower its recession speed should appear, reflecting the gradual braking effect of gravity over time. But when they analysed the data, they found the opposite. The distant supernovae were dimmer than expected, not because their light was weaker, but because they were farther away than the models predicted. That meant the universe had expanded more than it should have if the expansion was slowing. The only explanation was that the expansion was accelerating. It was an extraordinary result, so unexpected that the scientists themselves were hesitant to believe it at first. They checked their instruments, their calibrations, their assumptions. They compared notes across continents. But every analysis pointed to the same conclusion. The universe wasn't slowing down. It was picking up speed. Something was counteracting gravity on the larger scales, pushing galaxies apart faster as time went on. The discovery reshaped cosmology almost overnight. It meant that the dominant component of the universe wasn't matter, dark or otherwise, but something else entirely, something invisible, untouchable, and mysterious. To describe it, scientists revived an old term, the cosmological constant. Einstein had introduced it decades earlier to keep the universe static, then abandoned it when expansion was discovered. Now, it seemed, something like it was real after all, a kind of built-in energy associated with the fabric of space itself. That energy came to be known as dark energy. Dark energy isn't a substance we can detect directly. It doesn't shine, it doesn't clump, and it doesn't interact with matter in any known way except through gravity. Yet it behaves as if every bit of empty space carries a tiny, constant energy density, a uniform push that makes the universe expand faster over time. The more space there is, the more dark energy there seems to be, because the expansion itself creates more of the space that carries it. It's an elegant but unsettling feedback loop. As the universe grows, it creates more of the very thing that makes it grow faster. To make sense of it, you can think of dark energy not as a force acting within the universe, but as a property of the universe itself. It's part of the geometry of space-time, woven into the equations of general relativity. In that framework, mass and energy tell space how to curve, and space tells matter how to move. If space has an inherent energy, it can influence that curvature, effectively creating a repulsive gravitational effect on large scales. Instead of pulling things together, it pushes them apart. At first, this idea seemed too strange to be true. It violated intuition. How could space, which we think of as empty, have energy? And why would that energy cause acceleration rather than balance? But the data were undeniable. Observations of supernovae, combined with measurements of the cosmic microwave background and the large-scale distribution of galaxies, all pointed to the same conclusion. Roughly 70% of the total energy content of the universe comes from this mysterious form of energy that drives acceleration. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for less than 5%. The rest is dark matter and dark energy, invisible but essential to the universe's behavior. The realization was both thrilling and humbling. For centuries, humans had assumed that the visible cosmos was the main act, the stars, the galaxies, the things we can see and measure. Now, it turned out that all of that was just the tip of the iceberg. The universe we know is a thin veil over something much larger and more mysterious, governed by forces we can't yet explain. Even now, decades after its discovery, dark energy remains one of the greatest unsolved problems in physics. We don't know what it is, where it comes from, or whether it's truly constant. It might be an inherent feature of space-time, as Einstein suggested, or it might be something dynamic, a new kind of field that changes over time. It could be related to quantum fluctuations, or it could point to physics beyond our current understanding entirely. There are even models that suggest dark energy might eventually change sign, transforming from repulsive to attractive and altering the universe's fate once again. To appreciate just how strange this is, consider that even in the vacuum of empty space, quantum theory tells us energy never truly reaches zero. The quantum fields that fill the universe are always fluctuating, creating and annihilating virtual particles that momentarily exist before disappearing again. Those fluctuations give the vacuum a tiny energy, called the zero-point energy. If dark energy is related to this, it might explain why space itself seems to have a built-in expansion. The problem is that the numbers don't match. The amount of vacuum energy predicted by quantum theory is vastly higher, orders of magnitude greater than what we actually observe. Somewhere between quantum physics and cosmology, a profound mismatch remains. Still, whatever dark energy is, its effects are everywhere. Every second, the space between galaxies grows a little larger. Light travelling through the universe is stretched by that expansion, its wavelength lengthening as it crosses the growing fabric of space. The result is that distant galaxies fade not only because they're far away, but because their light is diluted by the universe's own growth. Over billions of years, entire regions of the cosmos will drift beyond our horizon, receding so quickly that their light will never reach us again. This accelerating expansion changes not only how we see the universe, but how we understand its future. If dark energy continues as it is, the universe will keep expanding faster and faster, galaxies will move out of sight, and the night sky will grow emptier. Stars will burn out, galaxies will fade, and eventually even the cosmic microwave background will be stretched until it's undetectable. The universe will become cold, dark, and quiet, not because it has collapsed, but because it has grown so vast that everything has drifted beyond everything else's reach. It's a haunting vision, but also a strangely peaceful one. The same force that drives galaxies apart also ensures that the cosmos will never collapse into chaos again. The universe is becoming more diffuse, more spacious, more silent, a slow unfolding into stillness. From the perspective of physics, that's simply entropy, the natural tendency for energy to spread out. But from a more reflective point of view, it feels like the continuation of a story that began with the universe's first breath of expansion. The outward motion that began in fire and density continues, gentler now but unstoppable. Even so, there are still unknowns. Some cosmologists have proposed that dark energy might not be constant, that it could change over time or even fluctuate in strength. If it were to grow stronger, the universe's acceleration could eventually tear apart even galaxies, stars and atoms in a scenario known as the Big Rip. If it were to weaken or reverse, gravity could one day reassert itself, slowing the expansion once more. For now, the evidence points to a steady, persistent acceleration, but the truth remains uncertain. In a way, that uncertainty is fitting. The universe has always resisted simplicity. Every time we think we've found the pattern, first a static cosmos, then an expanding one, then one that should slow, the universe reveals another layer. The discovery of dark energy reminds us that we're still newcomers in understanding the full picture. The cosmos is vast, ancient and subtle, and it continues to surprise even the most careful observers. If you were to watch the universe in fast motion, compressing billions of years into moments, you would see galaxies drifting away, clusters thinning, the cosmic web stretching like a net being pulled at its corners. Space itself would grow lighter, less dense, until the faint threads connecting galaxies faded from view. It's not that the universe is running away, it's that it's continuing what it has always done, expanding, evolving, responding to its own internal rules. The mystery that refused to slow down is, in some ways, a mirror of our own curiosity. We expected the universe to behave according to the patterns we could imagine, slowing, settling, balancing, but instead it showed us that there are deeper rhythms we haven't yet learned to hear. The same expansion that began at the dawn of time carries on, quietly accelerating, guided by an energy we can measure but not explain. And in that ongoing motion lies another layer of wonder. Because even as the universe expands faster and faster, it doesn't feel like chaos. It feels like continuity. The galaxies drift apart not in violence, but in silence, as if the cosmos itself is breathing out, slowly, endlessly. The same gentle rhythm that began in the earliest moments persists now, the same one that will continue long after the last stars have burned out. As scientists continue to measure that acceleration, refining their instruments, mapping galaxies billions of light years away, and testing theories of dark energy, the mystery deepens rather than diminishes. Every answer opens another question. What is space made of? Why does it have energy at all? Is the acceleration permanent, or just another phase in a universe that may yet surprise us again? For now, we only know this. The universe is not slowing down. It's still expanding, still accelerating, still unfolding its story. The outward motion that began with the Big Bang has never paused. It continues, steady and unstoppable, reshaping not only the cosmos but our understanding of what it means to live within something that is still growing, still changing, still carrying everything we know into an ever-widening future. And somewhere within that silent acceleration, gravity's gentle tug continues to work in the opposite direction, building stars, holding planets, shaping galaxies, reminding us that even as the universe expands, there's always a balance between what drifts apart and what comes together. That balance, delicate and ongoing, is what keeps the cosmos alive, even as it continues to stretch toward the unknown. By the late 1990s, when astronomers first realized that the universe was accelerating instead of slowing, a strange silence fell across cosmology. For generations, the laws of gravity had guided every understanding of the cosmos. It made sense that gravity should eventually pull everything back together. That was its nature. But here was evidence that gravity wasn't the only influence shaping the universe. Something unseen was at work, a quiet pressure that resisted gravity's pull. It didn't glow, it didn't radiate, it didn't gather like matter did. Yet it was everywhere, uniform and steady, woven into the fabric of reality itself. It was as if space had been hiding an invisible hand, one that didn't pull, but pushed. That hand was given a name, dark energy. It wasn't a discovery in the sense of finding a new particle or spotting a new star. It was a recognition that something fundamental was missing from our understanding. The equations that described the universe's expansion didn't balance unless this mysterious form of energy was included. There was no getting around it. Yeah, the space itself carried energy, or the data we were seeing were wrong, and the data verified again and again left no room for doubt. The universe was accelerating. The phrase dark energy might suggest something shadowy, perhaps something ominous, but it's not dark in the way a shadow is. It's called dark only because it can't be seen. It doesn't interact with the light, doesn't emit radiation, doesn't leave a direct trace. Its presence is inferred entirely from its effects. We see galaxies moving apart faster than gravity would allow, and we trace that motion back to something that must be fueling it. Like wind over water, we can't see the cause, but we can watch what it does. What's strange about dark energy is its uniformity. Unlike matter, which clumps into stars, planets, and galaxies, dark energy seems to be evenly distributed throughout all of space. Its density doesn't change as the universe expands. That means as space grows, there's simply more of it. In most cases, when something spreads out, its concentration decreases. But dark energy doesn't behave that way. It's as if space itself is creating energy as it expands, keeping its density constant. The result is an effect that becomes stronger over time. As more space appears, more dark energy appears with it, fueling the acceleration even further. To describe this mathematically, physicists use Einstein's equations of general relativity. Those equations link the geometry of space-time to the energy and matter it contains. When Einstein first developed them, they naturally predicted an expanding or contracting universe. To force them into a static solution, he added a term, the cosmological constant, representing a kind of repulsive energy that balanced gravity. He later abandoned it, calling it his greatest blunder. But after the discovery of the accelerating expansion, that same term returned as a natural explanation. Maybe Einstein's idea hadn't been wrong. Maybe space really did have a built-in energy, a property of existence itself. If dark energy is indeed the cosmological constant, it would mean the universe's acceleration is driven by a constant energy density of the vacuum, an energy inherent to empty space. But there's a problem. Quantum theory also predicts that the vacuum should have energy, arising from the constant flickering of virtual particles that appear and disappear everywhere. When physicists calculate how much energy that should amount to, the result is absurdly large, a value many orders of magnitude greater than what's actually observed. The discrepancy is so extreme that it's often called the worst theoretical prediction in physics. Somehow, between the mathematics of quantum fields and the measurements of the cosmos, a vast cancellation occurs, leaving behind just enough residual energy to drive cosmic acceleration. No one yet understands why. Other theories propose that dark energy isn't a constant at all, but a dynamic field, something that evolves with time. In that view, the energy of the vacuum could change as the universe expands, slowly decreasing or oscillating in strength. Some versions of this idea go further, suggesting that dark energy might even reverse its sign one day, transforming from a repulsive influence into an attractive one. If that happened, the universe's expansion could slow again or even collapse in on itself. These are possibilities for the far future, but they remind us that the story of the universe is not fixed. The forces shaping it might still be evolving. What makes dark energy so elusive is that it doesn't interact in any detectable way except through its effect on expansion. We can't capture it in a detector or observe it in a laboratory. All we can do is watch how the universe behaves and deduce what must be driving it. It's a bit like trying to understand the wind by looking only at the movement of clouds. You never see the air itself, but its presence is undeniable. Astronomers study dark energy by measuring the universe's expansion in as many ways as possible. They look at supernovae, the same kind that first revealed acceleration. They map the distribution of galaxies, looking for patterns in how they cluster over billions of years. They measure the cosmic microwave background, the leftover light from the Big Bang, to see how it has been stretched by expansion. All these independent lines of evidence point to the same conclusion. About 70% of the universe's total energy density is in this dark form. Ordinary matter, the atoms that make up everything we see, accounts for less than 5%. The rest, roughly a quarter, is dark matter, which exerts gravity but doesn't interact with light. It's strange to think that the universe is dominated by things we can't see or touch. When you look up at the night sky, every star, every glowing galaxy, every atom of light is part of a tiny minority. The vast majority of the universe's energy is hidden, invisible and silent, and yet it determines the fate of everything. Dark matter builds the scaffolding of the cosmos. Dark energy decides how fast that scaffolding stretches. The visible universe is just a thin layer painted across this invisible framework. For cosmologists, this realization is both humbling and exhilarating. It means that our most precise models of the universe depend on things we don't yet understand. We can write equations that describe how dark energy behaves, but we can't yet say what it is. Some compare it to the situation faced by Newton in his time. He could describe how gravity worked, but he couldn't explain why it existed. That deeper understanding came centuries later with Einstein. Perhaps, one day someone will do the same for dark energy, revealing the mechanism behind this invisible hand. In the meantime, scientists search for clues wherever they can. Some look for subtle signatures in the cosmic background radiation, hoping to find evidence of how dark energy has influenced the growth of structure over time. Others build massive telescopes and surveys to map galaxies across billions of light years, tracing the history of expansion with ever greater precision. New missions, like the Euclid telescope launched by the European Space Agency and NASA's Nancy Grace Roman Space Telescope, are designed specifically to probe dark energy's nature. Each new observation is a piece of a puzzle whose picture we can't yet see. Despite the mystery, there is something deeply elegant about the concept of dark energy. It ties together many aspects of physics that might otherwise seem unrelated, quantum fields, relativity, and cosmology, into a single phenomenon. It reminds us that even emptiness has properties. Space isn't nothing. It's a dynamic entity, capable of expanding, bending, and carrying energy. When you imagine the universe, you might think of it as a stage on which matter and energy perform, but in truth, the stage itself is part of the performance. Dark energy is the quiet rhythm that sets the tempo for everything else. It also changes how we think about the future. If dark energy remains constant, the universe will continue to expand at an ever-increasing rate. Galaxies will drift farther apart, and over unimaginable timescales, only the closest clusters will remain visible. Beyond them, space will grow so vast that distant galaxies will slip beyond the horizon, their light forever unreachable. The cosmic web will thin, the stars will burn out, and the universe will become colder and darker. It's a future not of collapse, but of isolation. Each surviving galaxy will become its own island universe, surrounded by darkness. It's a melancholy vision in some ways, but also a serene one. The same process that gives rise to galaxies and stars also ensures that they won't last forever. Everything the universe builds, it eventually lets drift away. On cosmic timescales, the expansion itself becomes the dominant feature, not the things within it, but the space between them. That space grows quietly, continuously, in a process that has no center and no edge. And yet, even if dark energy seems remote and abstract, it's part of the reality we inhabit. Every point in space, even the one you occupy right now, participates in the expansion. It's just that on local scales, gravity overwhelms it. The atoms in your body, the pull of the Earth, the orbit of the Moon, these are held together by forces far stronger than the faint push of dark energy. But beyond the boundaries of galaxies, in the vast stretches between clusters, dark energy dominates. It's the gentle pressure beneath all motion, the quiet expansion that carries everything forward. If you could watch the universe over billions of years in a single continuous view, you'd see that slow acceleration everywhere. Galaxies that once seemed close drift apart. The cosmic background light stretches further, its wavelengths lengthening as space expands. Structures that took eons to form begin to move beyond one another's reach. It isn't a dramatic process. It's steady, almost peaceful, like a tide that never stops rising. The invisible hand doesn't shove or pull, it simply keeps the universe unfolding. Scientists sometimes talk about the cosmological constant as a form of vacuum pressure, but it's not pressure in any familiar sense. It doesn't push outward from a center, it acts equally everywhere, so that every region of space feels the same acceleration relative to every other. This uniformity is what makes the expansion look the same from every vantage point. If you lived in a distant galaxy billions of light years away, you'd see the same pattern we see. Other galaxies moving away, the same cosmic acceleration. Every observer, no matter where they are, would feel as though they were at the center, not because there is one, but because the expansion happens everywhere at once. That equality is part of what makes dark energy so beautiful. It suggests that the universe doesn't have preferred places or privileged directions. The same laws hold everywhere. The same expansion unfolds everywhere. It's a kind of quiet fairness built into the fabric of existence, a consistency that connects every distant star, every point in space, every moment in time. Even if dark energy remains mysterious, its discovery has already deepened our appreciation for how little we truly know. It's a reminder that science isn't about reaching final answers, but about continually refining our understanding of what's possible. The universe has always been larger, stranger, and more subtle than our imagination. Every generation of discovery expands not just our sense of space, but our sense of humility. Some physicists suspect that dark energy may one day lead us to a new synthesis of theories, a bridge between quantum mechanics and general relativity, the two great frameworks that currently describe different sides of reality. If dark energy arises from the quantum vacuum, then its role in shaping the universe's geometry might point toward a deeper connection between the very large and the very small. Perhaps space and time themselves are emergent, built from something more fundamental that we haven't yet discovered. But until that day comes, dark energy remains an invisible hand, not seen, not touched, but always felt in the way galaxies drift, in the way light stretches, in the way the universe refuses to slow. It's the quietest influence imaginable, and yet it determines the fate of everything. Even now, as you sit here listening, the space around you is expanding, imperceptibly but surely, carried along by that same hidden energy. It doesn't make a sound, it doesn't glow. It simply is, steady and patient, the underlying pulse of a cosmos that has never stopped unfolding. When astronomers talk about the universe expanding, they aren't speaking in metaphors. The expansion is measurable, quantifiable, and as real as the orbit of the moon or the fall of a stone. But the scales involved are so vast, the time span so long, that the methods used to detect this expansion have to reach far beyond ordinary experience. Measuring how space itself stretches is one of the most delicate and precise undertakings in all of science. It means looking not at what moves in space, but at how space moves between the things that fill it. The first clues came, as we've already seen, from the light of distant galaxies. When Edwin Hubble compared their distances to their redshifts in the late 1920s, he found a simple, powerful relationship. The farther away a galaxy was, the faster it seemed to recede. That relationship, now known as Hubble's law, became the foundation of observational cosmology. The equation was straightforward enough. A galaxy's recession velocity equals its distance times a constant, the Hubble constant, which sets the rate of expansion. But behind that simplicity lies an enormous effort of measurement, refinement, and recalibration that has spanned nearly a century. Hubble's original value for that constant was much too high. His distances were underestimated because the tools of the time couldn't yet resolve individual stars in faraway galaxies. As a result, his estimate suggested the universe was only about 2 billion years old, younger than the Earth itself. It took decades of better telescopes, more accurate standard candles, and improved understanding of stellar physics to correct the scale. Today, we know the universe is about 13.8 billion years old, but even now, measuring the exact rate of expansion remains one of the most active and contentious areas of research in cosmology. The basic principle, though, hasn't changed. Light carries the history of motion. When a source of light moves away, its waves stretch, increasing their wavelength and shifting the light toward the red end of the spectrum. This redshift is a direct measure of how much the universe has expanded during the light's journey. By comparing the observed wavelengths of certain spectral lines, sharp features in a galaxy's light caused by specific elements, to their known laboratory values, astronomers can calculate the redshift precisely. The higher the redshift, the greater the distance and the older the light, but redshift alone isn't enough. To turn it into a distance, you need a reference, a way to know how bright something truly is. That's where standard candles come in. A standard candle is any object whose intrinsic luminosity is known. If you know how bright something actually is, and how bright it appears, You can calculate how far away it must be because brightness decreases with the square of distance. The trick is finding objects that are both bright enough to be seen across cosmic distances and uniform enough to serve as reliable yardsticks. For much of the 20th century, the most trusted standard candles were Cepheid variable stars that pulsate rhythmically, growing brighter and dimmer over time. The period of their pulsation is directly related to their intrinsic brightness. Measure the period and you know the luminosity. Compare it to the observed brightness and you get the distance. Cepheids allowed Hubble to measure nearby galaxies with unprecedented precision, and even now they remain one of the key rungs in what astronomers call the cosmic distance ladder, the chain of methods that link measurements from our solar neighbourhood to the farthest reaches of space. Beyond the reach of Cepheids, TPA supernova take over. These stellar explosions are so bright they can outshine entire galaxies, and their peak luminosity is remarkably consistent. By observing how quickly they fade, astronomers can standardize their brightness and use them as distance indicators across billions of light years. It was by observing such supernovae that the accelerating expansion of the universe was first discovered. Each of these methods builds on the next. Nearby distances are measured directly through parallax, the apparent shift in a star's position as the Earth moves around the Sun. Those measurements calibrate Cepheid variables, which in turn calibrate supernovae, which then extend to the farthest galaxies. The result is a continuous scale that spans from our immediate cosmic neighbourhood to the edge of the observable universe. But every step carries uncertainties, and those uncertainties accumulate. That's why different techniques sometimes give slightly different answers for the Hubble constant. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, suggest a slower rate of expansion, about 67 kilometers per second per megaparsec. Measurements based on Cepheids and supernovae in the local universe give a higher value, around 73. The discrepancy, known as the Hubble tension, has persisted for years and might hint at new physics. It could mean that the universe's expansion rate has changed more than expected, or that our understanding of dark energy, dark matter, or the early universe needs revision. Beyond standard candles, astronomers use another method known as standard rulers. Instead of measuring brightness, they measure the size of certain patterns imprinted in the distribution of galaxies. One such pattern is called baryon acoustic oscillations, subtle ripples in the density of matter left over from sound waves that travelled through the hot plasma of the early universe. These ripples set a characteristic scale, like the spacing between peaks on a graph, that can be used to measure distances. By mapping how that scale appears at different redshifts, scientists can trace how the universe's expansion has changed over time. The cosmic microwave background itself is the ultimate standard ruler. The tiny fluctuations in its temperature reveal the universe's geometry and density on the largest possible scales. By comparing those patterns to theoretical models, cosmologists can infer not only the expansion rate, but also the relative proportions of matter, and dark energy. The remarkable precision of these measurements is one of the triumphs of modern science. With instruments like the Planck satellite, scientists can determine the parameters of the universe to within a fraction of a percent, all by studying faint variations in radiation that's been travelling for nearly 14 billion years. Even so, measuring the cosmic stretch remains as much an art as a science. Every observation depends on interpretation. Light travels through an evolving universe, affected by gravity, dust, and time. Galaxies don't just move with the expansion, they also drift locally under the influence of nearby masses. Distinguishing those local motions from the global expansion requires statistical care and enormous amounts of data. That's why modern cosmology relies on surveys that chart millions of galaxies, building three-dimensional maps of the universe to reveal its large-scale structure. One of the most ambitious of these is the Sloan Digital Sky Survey, which over 2 decades has measured the positions and redshifts of millions of galaxies, tracing the web of cosmic structure across billions of light-years. Newer projects like the Dark Energy Survey, Euclid, and the Vera C. Rubin Observatory's Legacy Survey of Space and Time are pushing even deeper, mapping how galaxies have clustered and moved throughout cosmic history. Each new dataset refines our picture of how the universe has stretched from its hot, dense beginnings to its accelerating present. What's striking about all these methods is that they rely on light, the only messenger that crosses the vast emptiness of space. Every photon carries information about where and when it came from, and every spectrum encodes both motion and time. To measure the expansion of the universe is, in a sense, to read its autobiography written in light. The wavelengths of distant galaxies, the brightness of supernova, the patterns in the microwave background, all of it tells the same story of a cosmos that began small and hot, then stretched and cooled, and continues to stretch still. There's a quiet poetry in how that measurement works, even if the science behind it is precise. When light leaves a galaxy billions of years ago, it carries the imprint of that galaxy's motion through space. As it travels, space itself expands, stretching the light along with it. By the time it reaches us, its wavelength has lengthened, sometimes by factors of 1,000. In that redshift, we can read the history of the universe's growth. Each photon is like a tiny yardstick marking how much space has stretched since it began its journey. The challenge is that the universe doesn't expand at a steady rate. Gravity, radiation, and dark energy have all influenced its pace over time. In the early universe, radiation dominated, and expansion slowed rapidly as energy turned into matter. Later, matter dominated, and gravity's pull further decelerated the growth. Only in the last few billion years did dark energy begin to dominate, reversing the slowdown and causing acceleration. By combining observations from different epochs, nearby galaxies, distant quasars, the cosmic microwave background, astronomers can reconstruct that entire history, like piecing together a time-lapse of the universe evolving. Measuring the cosmic stretch also involves looking at how structures grow. Gravity pulls matter together, forming galaxies and clusters, while expansion pulls them apart. The balance between these processes depends on the density of matter and the strength of dark energy. By observing how clustered galaxies are at different distances, scientists can infer how fast the universe's structure has grown, a kind of fingerprint of the underlying physics. If dark energy was stronger or weaker in the past, it would leave a detectable imprint on those patterns. Modern cosmology, at its core, is about turning these subtle imprints into precise numbers. Each observation refines the parameters that define the universe, its age, its rate of expansion, its composition. The most widely used model today, called the lambda CDM model, includes just 6 key numbers that describe almost everything we can observe. Those numbers come directly from measurements of the cosmic stretch. It's astonishing to think that something as intangible as the expansion of space can be expressed in equations that fit the data so precisely, and yet the mystery of why it happens, what dark energy truly is, remains open. As technology advances, astronomers are beginning to measure the expansion directly in real time. Future experiments aim to detect the tiny changes in redshift that occur as galaxies drift away over decades of observation, a minuscule but measurable effect known as redshift drift. It's an almost unimaginable level of precision, detecting how the universe's expansion changes over human lifetimes. If achieved, it would turn the concept of cosmic stretching from an inferred process into something we can watch unfold. In another approach, scientists use gravitational waves, ripples in space-time produced by merging black holes and neutron stars, as a new kind of standard candle, or standard siren. The amplitude of these waves tells us how far away the source is, and their frequency shift reveals how fast the universe is expanding. Combining this with light-based observations could provide an independent check on the Hubble constant, helping to resolve the tension between different measurements. Each of these techniques represents humanity's attempt to grasp something vast and abstract. Measuring the expansion of the universe means reaching across billions of years of history, translating faint signals into understanding. It's a remarkable act of patience, collecting photons that have been travelling since before our planet existed, analysing their patterns, and using them to calculate how reality itself has stretched. And yet, for all its complexity, the outcome of these measurements is a single quiet truth. The universe is still growing. Every number, every graph, every redshift measurement points to the same conclusion. Space itself continues to expand faster than it once did, driven by an energy we cannot see. The galaxies are moving away not through space but with it, carried on the slow tide of an ever-widening cosmos. When we measure that stretch, we're not just quantifying a physical process, we're tracing the heartbeat of the universe, a rhythm so vast and slow that only by gathering light from billions of years can we begin to hear it. The cosmic stretch isn't something separate from us. It's happening everywhere, including here. Every particle, every atom, every quiet moment exists within that expansion. We are part of it, carried along in the same invisible motion that sweeps across galaxies and time itself. As astronomers continue refining these measurements, improving their precision, and comparing their results, they're not only learning how fast the universe expands, they're learning how that expansion shapes everything else. When we talk about the expansion of the universe, it's easy to imagine everything inside it expanding too. Galaxies stretching, stars drifting apart, planets slowly moving away from their suns. The phrase itself makes it sound like all distances, everywhere, are growing. But the truth is subtler. The universe expands, yes, but not in the way a balloon inflates or a sponge swells. The stretching of space happens on the larger scales, between clusters of galaxies, across the immense voids that span hundreds of millions of light years. On smaller scales, gravity and other forces hold things together so firmly that they resist the expansion completely. That distinction is one of the most important in cosmology, and it often surprises people. The Earth doesn't get farther from the Sun because of cosmic expansion. The atoms in your body don't stretch. Even galaxies themselves remain stable in size. The expansion of space is not a force acting on objects, but a feature of how distances change when there is nothing binding those objects together. On cosmic scales, the universe is like a vast network of islands, separated by an ever-widening ocean. The islands themselves, galaxies and clusters, stay intact, while the ocean between them keeps rising. To understand why this happens, it helps to think about how the expansion works. It isn't that galaxies are flying apart through space, like debris from an explosion. Instead, the very metric that defines space, the ruler by which distance is measured, is changing. When there's no force holding two regions of the universe together, that metric increases with time, making the distance between them grow. But within galaxies, gravity binds stars and gas tightly enough to counteract the expansion. The gravitational attraction between them far outweighs the gentle stretching of the universe. The same principle applies on smaller scales. The Sun's gravity holds the planets in orbit. The electromagnetic forces within atoms bind electrons to nuclei. The expansion of the universe is simply too weak to affect these local systems. To give a sense of scale, the rate of expansion today, known as the Hubble constant, corresponds to galaxies roughly 3 million light-years apart, receding from each other at about 70 kilometers per second. On the scale of the solar system, that effect is infinitesimally small, so small that it would take longer than the age of the universe for the distance between the Earth and the Sun to change by even the width of an atom. So, galaxies don't expand. They live within their own gravitational bubbles, largely insulated from the cosmic stretching around them. Yet the universe is not uniform, and that boundary between what expands and what doesn't isn't fixed. On the larger scales, between clusters, between the vast filaments of galaxies, expansion dominates. Over billions of years, those distances grow, and the galaxies that inhabit separate regions drift farther apart. The cosmic web itself, that immense lattice of matter shaped by gravity, is slowly being stretched. The nodes where galaxies cluster remain dense, but the voids between them widen, pulling the structure thinner and quieter as time goes on. This gradual widening changes how galaxies interact. In the early universe, when everything was closer together, collisions and mergers were common. Galaxies grew by merging, combining their stars and gas to form larger systems. The Milky Way itself was built this way, through countless mergers with smaller galaxies over billions of years. Even today, it continues to absorb small companions, and in several billion years, it will merge with the Andromeda Galaxy. But beyond our local group, mergers have become less frequent. The accelerated expansion of space has begun to isolate clusters from one another. The more time passes, the harder it becomes for gravity to bridge the growing gaps between them. Within each galaxy, though, gravity remains the dominant sculptor. Stars orbit in stable paths, bound by the combined mass of everything around them. The Milky Way's stars, for instance, move around its centre at hundreds of kilometres per second, their motion balanced by gravity's inward pull. These orbits aren't disturbed by the universe's overall expansion. Instead, galaxies evolve internally. Their stars age, die, and are replaced by new ones born from the gas left behind. Expansion affects them only indirectly, by changing the broader environment in which they live. In the early universe, when galaxies were closer together, they interacted more often. Gas could flow more easily from one to another, triggering waves of star formation. As expansion accelerates, those interactions grow rarer. The space between clusters becomes so wide that light itself takes longer to cross it, and eventually the galaxies outside our local region will fade from view entirely. In the far future, distant galaxies will slip beyond our cosmic horizon, moving away so fast that their light will never reach us again. From within the Milky Way, the night sky will look emptier, not because stars have disappeared, but because the expanding space has carried them beyond sight. That future is already beginning, though on a timescale so vast it's almost imperceptible. Astronomers can measure how galaxies cluster today compared to billions of years ago, and the pattern shows a clear trend. The large-scale structure of the universe is slowly freezing. Galaxies within a cluster remain bound, but clusters themselves drift apart. The cosmic web, once rich with connections, is stretching into ever thinner threads. The expansion acts like a slow, invisible wind, pushing the great tapestry of matter outward without disturbing the knots of gravity that hold it together. The galaxies that remain bound together, like those in our local group, will continue to interact for a very long time. When the Milky Way and Andromeda collide, their stars will mostly pass through one another because of the vast distances between them. But their gravitational fields will combine, reshaping both galaxies into a single larger system, a new elliptical galaxy that astronomers have already named Milkomeda. Around it, smaller dwarf galaxies will orbit, gradually merging or being stripped of their stars. Within that local island of gravity, life will continue as before, even as the universe beyond grows more distant. Eventually, though, the isolation will deepen. Billions of years from now, when dark energy has continued its steady work, the expansion will have accelerated so much that galaxies outside the local group will recede faster than light relative to us. That doesn't mean they're breaking any cosmic speed limit. It's the space between us that's stretching faster than light can cross it. But it does mean that we'll never be able to see them again. Their light, redshifted beyond any possible detection, will fade into invisibility. The observable universe will shrink not because space is contracting, but because expansion is carrying everything else away too quickly to be seen. In that distant era, the sky of the future will look very different. Instead of countless galaxies, only the stars of the merged Milkomeda will be visible, surrounded by the faint glow of nearby remnants. Astronomers living then, if there are any, will have no way of knowing that the universe was once filled with billions of other galaxies. They'll look up and see only their own island of stars with darkness beyond, without the faint whispers of the cosmic microwave background, or the faint red-shifted light of distant galaxies. They might never guess that space itself is expanding. The evidence we now take for granted will have slipped beyond reach. This isolation isn't tragic in any human sense. It's simply the natural evolution of an expanding cosmos. The same process that allows galaxies to form and evolve also ensures that, in the end, they drift apart. The balance between gravity and expansion determines how long they stay connected. Inside a galaxy, gravity wins. Between galaxies, expansion takes over. The universe is a dynamic balance of these two influences, one pulling together, the other pulling apart, and the outcome depends on scale. The delicate interplay between these forces also affects how galaxies evolve internally. For instance, the expansion of space governs the overall density of matter and gas available for star formation. In the early universe, when matter was denser, galaxies formed stars at furious rates. The sky would have glowed with young hot stars burning blue-white against the cosmic background. Over time, as expansion diluted the gas between galaxies, star formation slowed. The universe grew older, redder, quieter. Today, galaxies like the Milky Way still form new stars, but at a fraction of the rate they once did. The age of brilliant cosmic growth has passed, replaced by a slower, more measured rhythm. Even the light within galaxies carries the marks of expansion indirectly. The photons emitted by distant stars travel through expanding space, stretching in wavelength as they move. When we observe galaxies billions of light years away, we're seeing not only their past light, but also the effect of the universe's growth during that light's journey. The farther away we look, the younger the galaxies appear, frozen in earlier stages of evolution. It's like looking through a series of time layers, each one showing the universe at a different moment in its history. Some cosmologists describe this layering as a kind of natural archive. The universe itself records its past in light, and by studying galaxies at different distances, we can reconstruct how structure has changed over time. We see the early galaxies as compact, irregular clumps of stars, the middle-aged ones as spirals and ellipticals, and the modern ones as mature, stable systems. All of them exist in the same expanding framework, yet each occupies a different page in the cosmic story. That story is still being written. Even though dark energy has taken over as the dominant influence, gravity continues to shape galaxies internally. Stars still form, live, and die. Black holes continue to grow at their centres, consuming matter and releasing vast amounts of energy. Within those gravitational islands, the local universe remains dynamic, rich with motion and change. The expansion outside is silent and smooth, but inside galaxies, the dance of creation and destruction continues, driven by the same forces that have always governed matter and light. If we could zoom out far enough, beyond clusters, beyond superclusters, beyond the visible horizon, we would see that all of this complexity, all of this structure, is suspended within a vast and mostly empty expanse. The galaxies are like tiny jewels scattered across an ever-widening field, connected by threads so faint that they almost vanish in the growing darkness, and yet within each one, gravity keeps the stars together, holds the planets in their paths, and anchors the remnants of cosmic history. Expansion defines the stage, but gravity writes the detail. It's that balance between the smoothness of expansion and the clumping of matter that makes the universe as rich as it is. Too much gravity, and everything would collapse into black holes. Too much expansion, and nothing would have formed in the first place. The universe exists in the narrow space between those extremes, a self-regulating interplay of outward and inward motions. And while expansion continues on grand scales, it doesn't erase what gravity has built. It only sets the boundaries. The galaxies that exist now will endure, slowly aging, their stars dimming, they're gas consumed. Within them, new generations of stars will still appear for a while, fed by the remnants of earlier ones. But over trillions of years, even that process will fade. The last stars will cool into embers, the galaxies will dim, and the universe will slip into a long twilight. That future, quiet and cold as it may seem, is also part of the same expansion we observe today. The stretching of space ensures that everything has time to evolve, to live and change before the final stillness. Without expansion, the universe would have collapsed long ago. Because of it, galaxies had time to form, stars had time to burn, and life had time to appear on a small planet orbiting an ordinary star in one of those galaxies. Expansion and gravity, working together, created the conditions for everything we know. And even as the universe grows emptier, the traces of that balance remain. The galaxies that survive will carry within them the evidence of their origins, the ratios of elements forged in stars, the black holes that anchor their centres, the faint background light that once linked them to a larger whole. In that sense, galaxies are the fossils of a living universe, preserved by gravity even as expansion carries everything apart. As we continue to measure and model this expansion, we're not only describing how far galaxies move, or how quickly they drift away, we're describing the slow unfolding of time itself, a process that began with the first burst of light and continues in every direction. And within that expansion, each galaxy remains its own small universe, bound together by gravity, shining against the dark, carrying forward the story of how something can stay whole in a cosmos that never stops stretching. When we talk about the future of the universe, we're really talking about what happens to time on the largest possible scale. Every process, from the orbit of a planet to the drift of galaxies, is part of a larger sequence of cooling and spreading, the long consequence of the expansion that began at the beginning. The universe, as far as we can tell, has no edge and no outside, but it has a history, and that history points in a clear direction. Everything we observe suggests that expansion isn't stopping, it isn't even slowing, it's accelerating, driven by dark energy, the invisible pressure that pushes space apart. The question then is what that means for everything that exists within it. Right now, galaxies are bound together in clusters, each a kind of island of stars surrounded by the dark sea of space. Gravity holds them together tightly enough that expansion doesn't pull them apart. Our own Milky Way, along with the Andromeda Galaxy and a few dozen smaller companions, forms what astronomers call the local group, a small archipelago in the cosmic ocean. Beyond that, the Virgo cluster and the great web of galaxies stretch outward across billions of light years. But as the universe continues to expand, those distant clusters are drifting away. Light from them takes longer to reach us. Eventually, it will never reach us at all. This isn't a sudden change. It happens so slowly that on the scale of a single lifetime, or even the lifetime of civilization, it's invisible. But across billions of years, the effect becomes profound. The accelerated expansion means that distant galaxies will slip beyond the cosmic horizon, the boundary beyond which light can never reach us. The universe doesn't have a physical edge, but this horizon acts like one. Anything beyond it becomes forever unreachable. Even if you could travel at the speed of light, you would never catch up. For now, light from galaxies billions of light years away still reaches us. We see them as they were long ago, their light stretched by expansion into red and infrared wavelengths. But with every passing billion years, more of those galaxies disappear from view. Their light is stretched so much that it fades into the background, becoming part of the long, low hum of the universe's radiation. The night sky, which today contains billions of galaxies visible to large telescopes, will slowly darken. In the far future, only the galaxies within our local group will remain visible. Everything else will vanish beyond sight, not destroyed, but carried too far for light to ever bridge the gap again. That isolation marks the beginning of the universe's next great chapter. The local group of galaxies will merge into a single massive elliptical galaxy, the result of slow gravitational interactions that draw stars and gas together. Astronomers sometimes call this future galaxy Milkomeda. It will contain hundreds of billions of stars, many of them long-lived red dwarfs that can burn for trillions of years. Within that vast structure, stars will continue to form for a time, fed by gas left over from the merger. But even that process will eventually slow as the supply of gas runs out. Star formation, once common throughout the universe, will become rare. The same story will play out everywhere else, in other isolated clusters now beyond our sight. Each will become its own self-contained system of stars, black holes, and dark matter, evolving independently. As time passes, the remaining stars will age and die. The largest will end their lives as supernovae, scattering heavy elements into space. Smaller stars will cool quietly, turning into white dwarfs, dense, fading embers that no longer shine but still carry the heat of their former lives. After trillions of years, even those embers will cool, becoming cold, dark remnants called black dwarfs. No new stars will form, because there will be no gas left to make them. The universe will enter what physicists sometimes call the degenerate era, a time when almost all visible light has faded. The galaxies, once bright and crowded with stars, will be filled mostly with these quiet remnants: black dwarfs, neutron stars, and black holes. The cosmos will be dim, but not empty. Gravity will still hold these objects together, though the spaces between them will be vast. As even longer times pass, the slow processes of physics continue. White dwarfs that have cooled for trillions of years might eventually experience quantum tunneling events that trigger rare, faint bursts of fusion. A brief flash in the darkness, a last breath of starlight. Black holes will continue to dominate the centers of galaxies, consuming what matter remains. But even black holes aren't eternal. According to Stephen Hawking's work, they emit radiation, a faint glow caused by quantum effects near the event horizon. Over unimaginable timescales, this Hawking radiation causes black holes to lose mass and slowly evaporate. For the smallest black holes, this evaporation happens quickly by cosmic standards, but for the massive ones at the centers of galaxies, those millions or billions of times the Sun's mass, the process takes an astonishingly long time. Estimates suggest it could take 1067 years or more for them to evaporate completely. To put that number in perspective, the universe is only about 1010 years old now. By the time the last black holes disappear, more time will have passed than has ever existed since the beginning, by a factor so large it defies imagination. When that era arrives, there will be no stars, no galaxies shining, no black holes left to anchor them. The universe will be filled only with diffuse particles, photons, and neutrinos spread so thinly that the average density of matter will be nearly zero. Temperatures everywhere will approach absolute zero. The cosmic microwave background, already cooled to just a few degrees above that today, will stretch to wavelengths so long that it will be undetectable. Space will be dark, silent, and cold. This future is sometimes called the heat death of the universe. It doesn't mean fire or destruction. It means equilibrium, a state in which energy is so evenly distributed that no structure or activity can occur. In such a universe, nothing changes, because all differences have been erased. The cosmos, having expanded for so long, will have reached a kind of stillness, not because time stops, but because nothing within it can happen anymore. It's a strange ending for something that began in such brilliance. From the first light of the Big Bang to the fading glow of the last stars, the universe evolves from order into stillness. It's not a tragedy, though. It's simply the way energy behaves when given infinite time. Entropy, the gradual tendency toward disorder and equilibrium, isn't destruction. It's the natural direction of time itself. Expansion gives the universe room to evolve, but it also ensures that, eventually everything grows cold. Still, the story may not be quite that simple. The fate of the universe depends on the true nature of dark energy, and that's something we don't yet fully understand. If dark energy remains constant, the cosmological constant Einstein described, then the universe will indeed expand forever, growing ever colder. But if dark energy changes over time, other outcomes are possible. In one scenario, if dark energy gradually weakens, the expansion might slow and eventually stop. Gravity could then begin to pull everything back together, leading to a collapse, the so-called Big Crunch. In that version, the universe ends not in cold but in heat, with everything returning to the dense hot state from which it began. In another scenario, if dark energy grows stronger over time, the expansion could accelerate without limit. In that case, called the Big Rip, even galaxies, stars, and atoms would eventually be torn apart by the ever-increasing expansion. These possibilities are still speculative, and so far observations favour the gentler picture, a universe that expands forever, cooling and fading but never collapsing or ripping itself apart. Yet, even that endless expansion leaves open questions. Could new universes form from the remnants of this one? Could the vacuum of space itself decay, transforming into something entirely different? The more we learn, the more it seems that the story of the universe might not have a final page. On human timescales, these cosmic futures are beyond comprehension. The stars we see tonight will shine for millions or billions of years yet. The galaxies visible in our telescopes will drift apart, but slowly, far more slowly than any human history can encompass. The processes that lead to the universe's eventual stillness unfold over time spans that make the rise and fall of civilizations, even the entire life of our planet, seem instantaneous. That contrast between the human and the cosmic is part of what makes this story so compelling. We exist in a brief, bright window, a time when stars still burn, when galaxies still shine, when the universe is full of light. We arrived at a moment when it's possible to see and study the cosmos before it fades from view. In the deep future, no such view will be possible. The evidence of the Big Bang, the expansion, and the cosmic background radiation will all vanish. Any observers then will live in a universe that seems static and dark, unaware of the vast history that preceded them. It's strange to realize that the universe is, in a sense, temporary in its visible form. Everything we know, the colors of stars, the spiral arms of galaxies, the glow of nebulae, belongs to a finite era. The universe hasn't always looked like this, and it won't always look like this. We happen to exist in a moment when it's full of structure, light, and contrast. A moment when it's still young enough for stars to shine, but old enough for life to exist. The cosmic timeline is vast, but our own window of existence fits neatly within one of its most active chapters. Some physicists find this idea unsettling, others comforting. The universe's eventual quiet isn't a failure or an ending, but the natural consequence of time's passage. Every structure, from stars to galaxies to atoms, exists only because the universe has space and energy to work with. Once those have spread too thinly, the story simply continues in another form, not gone, just different. If the expansion truly goes on forever, there may never be a final moment, no boundary where time stops. The universe would keep stretching, its energy density approaching zero but never quite reaching it. In that sense, the end of everything isn't an event but a fading, an asymptotic approach to silence. The light never turns off all at once, it just dims, slowly, endlessly, into the dark. Even then, traces of the past will persist. The particles that once made up stars and galaxies will still exist, drifting through the vastness, carrying within them the memory of what came before. The laws of physics will still operate, even in the emptiness. The expansion itself will continue as a faint echo of the first moment, the initial burst of creation still rippling outward through time. For us, living in the age of light, The idea of such a distant future can feel abstract, but understanding it connects us to the deeper rhythm of the cosmos. The universe is not static. It's a process, a flow of energy from concentration to diffusion, from light to darkness. Everything within it, every star, every planet, every living being, participates in that flow. To know that is to see the continuity between the beginning and what comes after, to recognize that even as everything changes, it all follows the same quiet law of expansion and transformation. And that continuity, that smooth, patient evolution, continues to guide the universe now. The galaxies keep drifting apart. The stars keep burning. The expansion carries on, as it has since the beginning, setting the stage for everything that still exists and everything that is yet to come. When we look into the night sky, we're looking back in time. Every point of light that reaches us has travelled across a stretch of space that was smaller when it began its journey. The farther away something is, the longer its light has been travelling, and the younger the universe was when that light began its path. In this way, the entire sky becomes a kind of time machine. The faintest galaxies we can see are messengers from billions of years ago. Their light stretched and softened by the expansion of the universe. But there's a limit to how far that vision can reach. Beyond a certain distance, the universe becomes hidden, not because it ends, but because light hasn't had enough time to reach us since the beginning. This limit is what cosmologists call the observable universe. It's the region of space from which light has had time to travel to us since the Big Bang, about 13.8 billion years ago. But because space itself has been expanding all that time, the objects whose light we see from that distant past are now much farther away than they were when they emitted it. The radius of the observable universe isn't 13.8 billion light-years, it's roughly 46 billion. Beyond that, there are regions we can never observe, no matter how long we wait, because their light will never arrive. The expansion of space carries them away faster than light can bridge the growing distance. It's a strange boundary, this horizon. It doesn't mark an edge of the universe. There is no edge. But it does mark the edge of what can ever be known through observation. Everything beyond it is by definition invisible. That invisibility isn't just a matter of distance. It's built into the structure of space-time itself. The farther away a region is, the faster it recedes from us due to the expansion. Beyond a certain point, the recession speed exceeds the speed of light. Light from those regions still travels toward us, but the space in between grows faster than the light can cross. The photons stretch, redshift and fade until they vanish into wavelengths too long to detect. And yet, even though we can't see beyond this cosmic horizon, physics allows us to infer what lies there. The part of the universe we can observe seems smooth and uniform on large scales. The cosmic microwave background shows the same pattern of fluctuations in every direction, implying that the universe beyond our view is likely similar. The laws of physics appear consistent everywhere we can test them, suggesting they hold beyond our horizon as well. But likely is not the same as certain. For all we know, the unseen regions could be profoundly different, perhaps containing matter arranged in other structures, or even governed by different physical constants. That uncertainty invites both scientific curiosity and philosophical reflection. When we talk about the universe, we often mean the observable universe, because that's all we can study directly. But the real universe, the totality of everything that exists, might be far larger, perhaps infinitely larger. The observable portion could be just a small bubble in a vastly greater expanse. And if inflation theory is correct, that's exactly what it is. According to the theory of cosmic inflation, the universe expanded exponentially during its first fraction of a second, stretching quantum fluctuations into cosmic scales and smoothing out any irregularities. That rapid expansion was so extreme that regions once connected were flung beyond one another's horizons. Inflation ended locally, in our patch of space, allowing it to cool and form matter, but it may have continued elsewhere. In that case, The larger universe could consist of countless such patches, each a separate region where inflation stopped and a new universe began. Together they would form a multiverse, an enormous landscape of bubble universes, each potentially with its own properties, its own constants, its own version of physics. Whether or not that's true, the concept changes how we think about the horizon. It's not a wall, just a limit of perspective. The regions we can't see might be just like ours, or completely different. The important point is that the observable universe is not the whole universe. What we call the universe is simply the part that light has revealed to us so far. Beyond that, the cosmos may continue endlessly, without repetition, without boundary, an infinite fabric of space and time still unfolding. From a human standpoint, this scale is almost impossible to imagine. Even the observable universe is vast beyond comprehension, a sphere 46 billion light-years in every direction, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Beyond that, the unobservable regions multiply those numbers without end. Every direction we look could lead to more galaxies, more stars, more worlds, none of which we will ever see. The light from them is forever out of reach, not because it doesn't exist, but because the expansion of space keeps pushing it away faster than it can travel. It's humbling to realize that most of the universe is permanently hidden. The cosmic horizon isn't a limit we can overcome with better technology or longer waiting. It's a fundamental feature of an expanding space-time. No matter how advanced our instruments become, no telescope will ever pierce beyond that boundary. The information simply cannot reach us. We are forever confined to our own cosmic bubble, able to observe only a finite portion of an infinite whole. Still, there are ways to explore that unseen reality indirectly. By studying the patterns in the cosmic microwave background, scientists can learn about the conditions in regions that were once close to us before the expansion carried them away. Those patterns are like fingerprints left behind by the universe's earlier structure, imprinted before the horizon grew beyond them. Similarly, by mapping the large-scale distribution of galaxies, we can infer the shape and curvature of space itself. So far, every measurement suggests that the universe is flat, not curved inward like a sphere or outward like a saddle. That flatness implies that the total universe may be unimaginably larger than the observable part, possibly infinite. If the universe is infinite, then somewhere beyond our horizon, conditions identical to our own could exist simply by chance. There could be galaxies arranged exactly like the Milky Way, with planets indistinguishable from Earth, even people indistinguishable from us. Not because of science fiction, but because infinity allows every configuration to occur somewhere. The laws of probability make it inevitable. If space truly extends without end, every possible arrangement of matter repeats, though the copies are separated by distances so vast that they will never communicate. But infinity isn't necessary for mystery. Even in a finite universe, the unseen regions beyond our horizon are still real, still part of the same expanding space. The boundary between the observable and the unobservable shifts with time. As the universe ages, the cosmic horizon grows, allowing us to see slightly farther. But there's a catch. Because the expansion is accelerating, the rate at which distant galaxies slip beyond the horizon outpaces the rate at which new ones come into view. On balance, the observable universe is shrinking in terms of what we can ever see again. The light from distant galaxies we observe now is their last message to us. After that, they'll fade into permanent silence. The horizon isn't static, it's dynamic, always changing. Early in the universe's history, it was much smaller. As light travelled, it illuminated more of the cosmos, revealing new structures as time passed. But now, with acceleration taking over, the opposite is happening. The region we can observe is becoming more isolated, more self-contained. Eventually, it will include only the remnants of the local group, the merged galaxy and its satellites, surrounded by blackness. Everything else will be beyond communication, locked behind a horizon that grows faster than any signal can cross. This evolving isolation raises profound questions about what it means to exist within a universe that's mostly inaccessible. For humans, used to exploring and mapping, it's strange to think that most of reality is permanently beyond reach. Yet, from a physical point of view, that horizon doesn't separate us from the rest of the universe. It's simply a boundary in time. The light from those regions is still travelling, but will never be around to receive it. The cosmos beyond the horizon continues its own history, unaffected by whether we see it or not. In that sense, the horizon is less a limitation than a reminder. It reminds us that observation is always local, that every perspective in the universe has its own horizon. If you were in a distant galaxy billions of light years away, you would have your own sphere of the observable universe, centered on you. Our horizons wouldn't overlap, but both would describe the same universe, just from different vantage points. Every observer everywhere lives at the center of their own visible cosmos, surrounded by the parts of reality that light has revealed to them. That symmetry is one of the most elegant aspects of cosmology. It means there's no privileged center of the universe, no edge, no up or down. The expansion looks the same from every point because it happens everywhere at once. The horizon isn't a wall surrounding a center. It's a feature that exists for every observer. The universe, in that sense, is a web of overlapping horizons, each defined by the limits of light and time. Thinking about this leads naturally to the question of what lies truly beyond. Not just beyond what we can see, but beyond what exists. Could there be regions where physics operates differently, where the constants of nature vary, or where space itself is shaped in other ways? If inflation produced multiple regions of space-time, each emerging from different quantum conditions, then each might have its own laws. Some might expand forever, others might collapse, some might never form galaxies at all. In that view, our observable universe is just one pocket in an infinite mosaic of possibilities. Of course, such ideas remain speculative. There's no direct evidence of other universes, and perhaps there never can be. But the mathematics of cosmology allows them, and some aspects of quantum theory seem to hint in that direction. Whether or not they exist, the concept highlights how limited our perspective is. What we call everything is only a small part of something larger, perhaps much larger than we can imagine. And yet within our horizon, the universe feels complete. The same physical laws apply everywhere we can test them. The same patterns of matter repeat across the sky. The same expansion stretches all directions equally. From within our vantage point, the cosmos feels whole, coherent, and self-contained. The fact that there might be more beyond what we can see doesn't diminish that completeness. It only adds depth to it. The universe doesn't need to end for mystery to exist. It only needs to keep going beyond our light's reach. Even now, light from the most distant galaxies continues its long journey toward us. Some of it has been travelling for almost the entire age of the universe. When it finally arrives, it carries information about regions once unimaginably far away, letting us glimpse just a little more of what lies beyond. Each photon that reaches us pushes the horizon of understanding slightly farther. The boundary moves, not because the universe changes, but because our light has had more time to cross it. Every new observation is a conversation with the past, a message from places that once shared our neighbourhood before expansion carried them away. If you step outside on a clear night and look at the stars, you're already seeing across that deep ocean of time. The starlight falling on your eyes has crossed vast distances of space, travelling through the same expanding fabric that connects everything. The visible sky is just the nearest layer of a much greater whole, a local expression of a universal geometry that extends endlessly. Beyond the visible stars lie galaxies, beyond the galaxies lie clusters, and beyond those lies everything else, the unlit, unobserved, unreachable parts of the cosmos, still expanding, still moving farther away. The horizon reminds us that knowledge itself has limits, but also that those limits are temporary in a relative sense. Every generation of observers sees a little farther than the last. We may never see beyond the ultimate boundary, but we can keep approaching it, one photon at a time. The horizon grows not because the universe is holding something back, but because it's giving us more space to explore, more distance for light to travel, more time to wonder. And as the expansion continues, carrying more and more of the universe beyond reach, the horizon becomes both a scientific fact and a kind of metaphor, a symbol of how perception works in an infinite cosmos. We can never see all of it, but that doesn't mean it isn't there. The unseen universe, stretching beyond what light can tell us, is as real as the one we know. It's the quiet continuation of everything we can measure, the extension of the same pattern into the darkness. That unseen region isn't a mystery to be solved so much as a reality to be accepted. The universe doesn't end where our instruments fail. It keeps going, expanding, cooling, carrying galaxies and light into the distance. The horizon isn't a wall, it's a mirror of time showing us the edge of what has been revealed so far. Beyond it, the same expansion continues, unseen but certain, writing the next pages of a story we can only imagine. For most of cosmic history, expansion has been a silent, invisible process. It doesn't make a sound, doesn't leave a mark that our senses can detect. The stars rise and set, the planets move through their orbits, and nothing in our daily lives seems to hint that space itself is stretching. Yet it's happening everywhere, all the time. Every second the fabric of the universe grows, and every moment galaxies drift a little farther apart. To us, the effect is so distant that it might as well belong to another reality. But the truth is that we live inside that expansion. Every breath, every heartbeat, every passing day unfolds within a cosmos that is still growing. When scientists describe the expansion of the universe, they're talking about a process measured in billions of years and trillions of kilometers. On that scale, human concerns seem microscopic. The Earth, the solar system, even our entire galaxy are small islands in a sea whose size defies imagination. But scale doesn't determine importance. To understand what cosmic expansion means, we have to translate it from the language of astronomy into something that can be felt, into what it means to live inside a universe that will never stop changing. The first thing to realize is that expansion isn't a motion through space, but a change in the geometry of space itself. The galaxies aren't flying apart through emptiness. The space between them is stretching. This means there's no center and no edge. The universe doesn't expand into anything. It simply becomes larger from within. Every observer, no matter where they are, sees other galaxies moving away, and every point in space experiences the same growth. From any perspective, it looks as if the expansion radiates outward, but that's only because space itself is expanding everywhere at once. For humans, the effect is impossible to sense directly, because on small scales, other forces are vastly stronger. The electromagnetic attraction that holds atoms together, the gravity that binds planets to stars, these completely overpower the faint pull of expansion. The rate of expansion today is about 70 kilometers per second per megaparsec, which means that two galaxies separated by 1 million parsecs, roughly 3 million light-years, move apart at 70 kilometers per second. Within a galaxy, where distances are measured in thousands of light-years, the expansion's effect is practically zero. The solar system, bound by the sun's gravity, doesn't stretch, neither do our atoms, so the expansion of the universe doesn't tug at our bodies or separate us from the ground beneath our feet. It's not something that affects us physically in any direct way, but in a larger sense we are deeply connected to it. Every atom that makes up the human body was forged in the cores of stars, and those stars formed within galaxies shaped by the universe's expansion. The very fact that we exist at all depends on the delicate balance between gravity pulling matter together and the expansion pulling it apart. If expansion had been too fast, matter would never have gathered into stars or planets, If it had been too slow, the universe would have collapsed before life could form. Somewhere between those extremes, there was just enough time and just enough space for complexity to appear. That balance means that every part of human existence, from the chemistry of our blood to the structure of our DNA, is a local expression of a cosmic process. We live in the quiet middle age of the universe, long after its violent beginnings but long before its distant end. The stars are still burning. The galaxies are still visible. Expansion continues, but gently. We inhabit a moment when the universe is vast enough to host life, yet still luminous enough to be seen. This moment won't last forever, but it's ours. A brief bright interlude in a story that stretches across billions of years. Thinking about this scale can feel dizzying. The numbers are too large to hold in the mind. But one of the quiet truths of cosmology is that understanding the universe doesn't require leaving the human scale behind. The same physical laws that govern the motion of galaxies also govern the atoms in our hands. The same equations that describe cosmic expansion also describe the way time flows, the way energy moves, the way matter interacts. The universe isn't divided between the vast and the small. It's one continuous whole, and we are part of its continuity. That idea is easier to grasp when you think about light. Every photon you see, from the glow of a candle to the shimmer of the stars, travels through the same expanding space that carries galaxies apart. Light interacts with expansion directly. As it moves through space, its wavelength stretches, growing longer, redder, softer. The light that leaves a distant galaxy billions of years ago arrives here transformed by that journey. The light that leaves the sun takes just over 8 minutes to reach us, but even in that brief span, it travels through a universe that's ever so slightly larger than when it began. Every ray of sunlight carries within it the imprint of cosmic motion. In that sense, expansion is something we experience constantly, even if we don't notice it. The sky itself is a record of expansion, written in the shifting colour and energy of light. Every distant star, every faint galaxy we can see has been stretched by the growth of space. The universe doesn't need to announce its motion. It leaves quiet evidence everywhere. In the way light cools, in the way radiation thins, in the way time itself flows. There's also a psychological aspect to thinking about expansion on the human scale. Knowing that everything around us is part of a universe that's been growing for nearly 14 billion years changes how we think about place and time. It gives meaning to smallness. When we look at the night sky, we're seeing the past, not metaphorically, but literally. The light from some of those stars began its journey before humans existed, before the Earth had taken its present form. The photons that enter your eyes tonight have crossed stretches of space that have expanded and cooled since they left their source. They bring with them a direct connection to cosmic history. That connection can be strangely grounding. In everyday life, our attention is pulled toward the immediate: work, sound, movement, the small circle of the present. But the universe around us operates on scales that dwarf all that urgency. The expansion reminds us that everything we do happens within a much larger frame, one that doesn't rush or compete, one that simply unfolds. The universe doesn't hurry. Its changes are steady, measured in billions of years. When we look outward, we are looking at a timeline so long that our entire species appears in it as a flicker. Yet that flicker is part of the whole, no less real for its brevity. In that perspective, even stillness becomes part of motion. The atoms that make up our bodies were created in stars, scattered through supernovae, gathered into new systems and finally assembled into life. The air we breathe, the water we drink, the calcium in our bones, all of it is recycled material from earlier generations of stars, held together by gravity and time. The expansion of the universe made room for that cycle to happen. It allowed the stars to form and die, to scatter their elements, to enrich the cosmos. Without expansion, everything would have remained too dense, too hot, too brief. There's a quiet irony in that. The same process that drives galaxies apart also made it possible for anything to exist at all. Expansion created distance, and in that distance, structure could form. The gaps between particles, between atoms, between stars, those spaces are what allow complexity. In a universe without space, there would be no matter, no chemistry, no life. The emptiness we see when we look up isn't absence. It's the condition that allows everything else to be. Even the flow of time is linked to expansion. The universe's growth sets a direction for time to move, from denser and hotter to cooler and more diffuse. The passage of time we experience is the local manifestation of that cosmic asymmetry. We live in a universe that expands, and because of that, entropy increases, complexity evolves, and time moves forward. Every moment you experience is connected to that larger process. Each heartbeat, each thought, unfolds in a universe whose background is stretching and cooling, setting the tempo of reality itself. There's something deeply comforting in this connection. Expansion might seem remote, but it's the thread that ties everything together. It links the first light of the cosmos to the present moment. It's the reason there are stars to shine, atoms to breathe, and time to live within. Even though it happens on scales far beyond human reach, it's not separate from us. We are part of it, expressions of the same physical laws that drive galaxies apart and stars together. Thinking of the universe this way changes what scale means. On one hand, we are tiny, so small compared to the cosmic web that our entire planet is like a mote of dust in a beam of light. On the other hand, we are the only part of that web, as far as we know, that can look back and see the whole. Consciousness gives the universe a way to know itself. The atoms scattered by expansion have arranged themselves, for a time, into something that can measure and understand that very expansion. In a literal sense, we are the universe becoming aware of its own motion. That realization doesn't diminish the vastness of the cosmos, it makes it intimate. The expansion isn't happening somewhere else. It's happening here too, in the same reality we inhabit. The stars are part of it, but so are we. When you look at a distant galaxy through a telescope, you're not looking outward as much as backward, seeing the past of the same space that now surrounds you. The light that reaches your eyes has travelled through the same universe you live in, stretched by the same expansion that carries everything forward. In daily life, it's easy to forget that. The world feels solid, fixed, immediate, yet all of it exists within a larger flow. The ground beneath your feet is part of a planet orbiting a star, inside a galaxy moving through an expanding universe. Even standing still, you are carried along by motion, not just the rotation of the Earth or the orbit around the Sun, but by the expansion of space itself. The entire fabric of existence is in motion, and so are we, in ways that are too vast to feel. That motion has meaning beyond physics. It gives context to everything we do. Every human story, every memory, every moment of awareness happens within the brief span of a universe that is still unfolding. The same expansion that defines galaxies also defines eras, the rise and fall of stars, the emergence of life. It sets the scale not only of space but of time. In the endless widening of the cosmos, our short lives are not insignificant. They're the precise scale at which awareness becomes possible. We are small enough to fit within a galaxy, but complex enough to understand the forces that shape it. In that sense, the human scale of expansion isn't about measuring distances or calculating rates. It's about recognizing that the same laws that govern the largest things also govern us. It's about understanding that our sense of time, our ability to look up and wonder, comes from the same expansion that drives galaxies apart. It's about realizing that even though we're fragile and brief, we belong fully to the universe's story, not apart from it, but within it. Every step you take, every breath you draw, happens in a universe that is still expanding. Every night sky you look at is part of that ongoing motion. The cosmic horizon may define the limits of what we can see, But within those limits, we have the chance to understand. That understanding doesn't stop the expansion, but it changes our place within it. It turns the vast, cold distances into something meaningful, a context for our own existence, a reminder that the same space stretching between galaxies also exists within us. And as the expansion continues, carrying galaxies farther apart, the human mind continues to reach outward too, searching for patterns, for meaning, for connection across that vastness. The same curiosity that built telescopes and equations is part of the same expansion, not physical, but intellectual, a widening of awareness that mirrors the universe's own growth. That widening continues still. Each discovery extends our understanding, each observation pushes the boundary of what we know, and beyond that, the expansion itself continues to unfold, quietly, steadily, carrying all things forward. From the smallest atom to the largest galaxy, everything participates in that motion, including us. If you step outside on a clear night and look up at the sky, it's easy to think of it as still. The stars seem fixed, the darkness around them unchanging. The air is quiet, the world is small, and nothing appears to move except for the slow turning of the earth. But that stillness is an illusion. Every point of light above you is moving away. Every patch of space between them is growing. Even as you stand there, the universe is expanding. It's not loud or visible. It doesn't stir the air or pull at your feet. But it's there, the slow, steady breathing of the cosmos, the same rhythm that has been unfolding since the beginning of time. That expansion doesn't happen in bursts. It isn't a sudden process. It's continuous and patient, like the tide moving across a shore too vast to see. Every second, galaxies drift imperceptibly farther apart. Every ray of light stretches a little longer. Every moment adds to the total distance between things. It's a motion without wind or sound, but it shapes everything. The stars, the planets, the space between atoms. All of it exists within this quiet expansion. And even though it's invisible, it defines what it means for time to move forward. The universe is not static, not frozen, not fixed in size. It has been changing since the first moment of creation, and it will keep changing long after the last star has gone dark. The same processes that allowed galaxies to form still guide the cosmos now. Gravity pulls matter together. Dark energy pushes it apart. Between those two, the balance keeps shifting, and in that shifting lies the flow of history. What we call time is the unfolding of that balance, the gradual transformation of energy and space as the universe continues to breathe outward. It's difficult to imagine such motion because it happens on scales beyond comprehension. We live within it, but we don't feel it. The room you sit in doesn't stretch. The world doesn't drift apart. On the human scale, the expansion is drowned out by stronger forces. Gravity, electromagnetism, the bonds that hold everything together. But the absence of sensation doesn't mean the absence of motion. Expansion isn't something that passes us by. It's the backdrop of existence itself. It is the environment in which every moment, every event, every life occurs. That awareness can change how we see the universe. When you look up at the stars, you're not seeing a static picture. You're seeing a snapshot of something in motion, a frame in a film that has been running for billions of years. The light from those stars has been travelling through expanding space, its wavelength stretched by that journey. The darkness between them is not empty, but alive with that slow, steady growth. Even the silence of the sky is full of movement, the quiet continuation of the same breath that began in the first instant of creation. The idea of the universe breathing isn't just a metaphor. The expansion really does have a rhythm, a measurable pace. It began rapidly, slowed under gravity's pull, then accelerated again as dark energy took over. It's not a perfect cycle. It doesn't inhale and exhale in the way living beings do. But the pattern of expansion and balance has a kind of pulse to it. It's the rhythm of change, the tempo of evolution on the largest possible scale. It's the background motion that carries everything, including us, forward through time. We exist inside that motion. Every moment of life takes place within it. Every thought, every word, every heartbeat happens in a universe that's growing, just a little larger than it was a moment before. The fact that we can even know this is remarkable. For most of human history, the sky seemed eternal, its lights unchanging. The discovery that it is not, that the universe itself is dynamic, expanding, and alive with invisible energy, is one of the most profound insights ever reached. It changes how we think about existence. It replaces the image of a fixed cosmos with one that's evolving, not toward an ending, but toward a continual transformation. The universe doesn't expand for a reason, just as gravity doesn't pull for a reason. It's simply what space does under the conditions set by its own laws. But in that simplicity lies something beautiful. The same equations that describe the orbit of a planet also describe the stretching of galaxies. The same mathematics that explains a falling apple also governs the evolution of the cosmos. There's a continuity that runs from the smallest motion to the largest. It's not personal, but it's complete. It connects everything, from the atoms in your body to the light from the most distant quasar. Thinking about that connection can make the universe feel less remote. It's not an external thing, not a place that surrounds us from the outside. It's the same process that includes us. The atoms in your skin, the calcium in your bones, the carbon in your cells. All of them were forged in stars scattered by supernova and drawn together by gravity in the aftermath of expansion. The universe didn't just create the conditions for life, it became life. Through us, through our awareness, the universe is watching its own expansion, tracing its own breath. That awareness might be brief on the cosmic scale, but it's part of the whole. The universe doesn't notice time in human terms. It doesn't rush. Its processes take billions of years, and even then, it's not finished. The stars we see now are the temporary product of hydrogen turning into light, a phase that will eventually end but that represents only one stage in a much longer sequence. The galaxies are temporary too, just patterns in the larger motion. Everything that exists now is part of a flow that began long before and will continue long after. The expansion isn't about permanence or impermanence, it's about continuity. The fact that we can feel awe in the face of that continuity is itself extraordinary. Somewhere in the vastness, matter became complex enough to wonder what it is. The universe gave rise to beings capable of noticing that it's expanding. That act of noticing doesn't change the cosmos, but it adds a new dimension to it, a moment of self-reflection written into the vast unfolding of space. We're part of the mechanism by which the universe observes itself. In that sense, when we say the universe is still breathing, we're describing more than physical expansion. We're describing the ongoing presence of motion and awareness. The galaxies move, the light stretches, the stars evolve, and we, made of the same matter, continue to think and feel within that flow. The breath of the universe isn't separate from the breath of life. It's the same process, scaled differently, following the same physical principles that allow energy to move and matter to change. If you could somehow step outside time and watch the universe unfold in a single instant, from its beginning to its distant future, it would look like a single continuous pulse. Energy expanding, condensing, radiating and expanding again. Stars igniting, burning and fading. Matter forming and dissolving. That pulse would never truly stop. It would just change form. Even in the far future, when the stars are gone and space grows cold, the expansion will continue, carrying forward the same momentum that began with the Big Bang. The breath will go on, even if the light goes out. To think of the universe this way is to realize that endings aren't really endings. The fading of stars, the cooling of space, the eventual quiet of the cosmos. These aren't closures, but transitions. The universe doesn't finish. It changes state. energy transforms into new forms, structure dissolves into new arrangements, and the expansion continues. What seems like silence is still motion. What seems like emptiness is still full of the same underlying energy that has always been there. In our own lives, we experience the same pattern on smaller scales. Things change, decay, transform, and continue. The rhythm of breathing, the passing of days, the movement of thought, all are microcosms of the same expansion. The universe isn't something distant that happens elsewhere. It's something that includes us, operating through us in miniature. We are part of its pattern, woven from the same processes that shape galaxies. The expansion gives the universe its shape, but gravity gives it structure. The balance between them gives it life. The breathing of space isn't chaotic. It's ordered by laws that hold consistently across all scales. Those laws are what make existence stable enough for life to arise and long enough for thought to develop. When we speak of the universe breathing, we're really speaking of the persistence of those laws, the quiet, continuous unfolding of reality according to principles that don't waver. And while we may never see the entire universe, the part we do see is enough to understand that the whole is coherent. The galaxies, the light, the background radiation, the faint patterns in the sky, all of them are signs of the same expanding space, the same continuous motion. Every observation confirms it. Every measurement fits. The universe isn't random in its expansion. It's precise, patterned, and self-consistent. The breath has a rhythm that can be calculated, a tempo that can be measured, and yet it still feels, somehow, alive. For a moment, it's worth thinking about what it means that this expansion will never stop. It means that the universe is a process without completion. There is no final form, no ultimate state in which everything settles forever. The cosmos keeps opening, keeps unfolding, creating more distance, more time, more room for whatever comes next. We live within that process, and we participate in it. Every thought, every life, every star, every photon is part of that same continuous unfolding. From that perspective, the universe isn't a static thing to be described, but an ongoing event to be experienced. Its expansion isn't just a fact of physics. It's the condition that makes everything possible. It allows time to exist. It gives the future space to arrive. It provides the canvas on which everything happens. Without expansion, there would be no sequence, no cause and effect, no evolution. Expansion is what allows the story to continue. So when we say the universe is still breathing, what we really mean is that it's still becoming. The expansion hasn't stopped. The process of creation is ongoing. It might be slower now than it was at the beginning, but it's not finished. The galaxies continue to drift. The light continues to stretch, and time continues to open new possibilities. The same motion that began the first atoms continues through everything that exists now. Standing beneath the night sky, it's possible to feel that continuity directly, even without understanding the details. The stars above you are ancient, but their light is still new in your eyes. The space between them is vast, but it connects to the same space around you. Every breath you take exchanges atoms that have been part of stars, part of planets, part of other living beings. The universe's expansion isn't something that happens outside you, it's something that happens through you. And as you breathe in, you're part of that same rhythm, a smaller echo of the universe's own motion, a reflection of the same laws that guide galaxies. The expansion continues, carrying everything forward, gently, silently, endlessly. Space stretches, light travels, time flows. The universe doesn't rest. It only moves at its own pace, steady and patient. The breath never stops. Even in the farthest future, when the stars fade and the night sky grows empty, that motion will still go on. The universe will still be expanding, still breathing in its own quiet way. There will still be space. There will still be time. there will still be the slow unfolding of the same laws that have shaped everything since the beginning. And within that endless expansion, there will always remain the trace of what came before, the memory of light, the echo of stars, the lingering awareness that the universe, even in silence, is still alive. And so it continues, always expanding, always moving forward, the same invisible rhythm beneath everything, the universe still breathing,